morning, all, and welcome back for day 2 of the 2023 first annual international online training course that myself and Gustavo are hosting. Yesterday, was a full 3 hours packed full of information regarding fluid level analysis methods, and we expect that we have just as much information in the same amount of time as we did yesterday. And today we're going to be talking about dynamometer measurement. And so, without further ado, I'm going to go ahead and reiterate and reemphasize that the chat will be open during the training course. So that way we can ultimately take your questions, and at the end of the training, we will ultimately answer those questions, make sure that we get everyone taken care of. Now, one thing that we wanted to point out is that both Gustavo and our email address is located at the bottom of the screen. If you have a question that you think of after the training, or even you want to send us some data to take a look at and help you evaluate as you learn how to interpret, our email address is there at the bottom of the screen. Feel free to shoot us an email. We'd love to hear from you and help you out as you learn this process of analysis. Now, one of the things that we're going to start out doing each morning, because we're going to have people that are joining for the first time as they're joining for a specific topic, is I want to start out the training the same way we did yesterday. And I want to make sure that everyone understands the resources that they have available on our website. And so with that, I would like to open up our website. And as I directed you yesterday, our website, www.echometer.com, you can go to. And there's a lot of information at your disposal, from information about products, software, Ask Echometer sessions, which we talked about a little bit yesterday. Those Ask Echometer sessions are packed full of information that you can watch presentations free. That's most important, to your convenience. So with that, let's dive into a little bit on the website. And so one of the things that you can see, and we noted too yesterday, is that we have a full availability of products on the website. Now, today we're going to be talking about dynamometer sensors. However, if you need anything from gas gun diagrams, that can be located on the website. You navigate to gas guns, click on your particular gas gun that you're operating, and scroll down, and you can click on the drawing to navigate to the point where you can make repairs in the field or ultimately order a part. Now, because we're staying on the topic of dynamometer today, I wanted to point you to the portion of the website in which you can find dynamometer sensors. And you're going to navigate from products to transducers. And here you will find all the different sensors that we offer for dynamometer acquisition, being as foreshadowing, the 30K load cell, the 4-inch Horseshoe transducer, the 5-inch Horseshoe transducer, the 50K load cell, both PRTs, wired and wireless, as well as power probes, pressure transducers, and other pieces of equipment that we'll introduce today. So you have all of that at your disposal with detailed information about each individual transducer by clicking on the link. It's very, very detail oriented. And if you have any other questions, like I directed you at the beginning, be sure to send Gustavo or I an email about that. Now, as we talked about yesterday, Echometer software is always free to download. Okay, you can go to the website and you can ultimately download our latest TAM version of software, 1856, which we talked about in detail yesterday. You can also download older versions of software, such as Total Well Management, AWP, if you're using the Model M strip chart recorder, as well as our free rod design software, QRod, and the gas separator simulator. So all of that's available for download. We had introduced Ask Echometer yesterday, and as I said earlier, that is ultimately a great place to go in and to really spend time in some of these presentations and being able to pause, stop, play, because the links are on YouTube. You can go in there and learn about different topics. One of the things that we won't get into as much today, but something that is related to dynamometer, is motor power current analysis while utilizing the dynamometer sensors. And so that may be something that you want to look at and learn a little bit more about. And I would direct you to that Ask Echometer session. As we talked about yesterday, we also have a full docket of technical papers that you can review on many different topics over many years of study. We also have a training schedule in all of our courses that we offer here free to attend in the US, as well as the international trainings that we hope to continue to host via Zoom. So there's a lot of information, and I invite you to explore the website to make sure that you take advantage of everything that is available for you. So without further ado, let's go ahead and let's get into the presentation this morning. And the way that I felt that we should structure this conversation on dynamometer data is that before we actually get into dynamometer interpretation, you actually need to understand what sensors and when you would want to use those particular sensors and to acquire that dynamometer data. Echometer makes several different dynamometer sensors, and they're all great, but they all have good applications for when they need to be used. And so during this presentation, kind of what I'm going to introduce is I'm going to introduce the individual sensors. I'm going to talk about the pros, the cons, and when you might want to use that particular sensor, and kind of understand the basis to build the framework for the fundamentals, which will be discussed here when Gustavo speaks in a little while. We'll also go through the procedures on how to acquire dynamometer data with the PRT, the polish rod transducer, which we'll talk about, as well as the HT, which is the horseshoe transducer. And we'll go through the procedures so that we understand step by step how this data is acquired in the field. So with that, let's talk about why would we run a dynamometer test? Okay, there's some basic questions that we can answer by running this particular test. First and foremost, I would think, what is my pump fillage? Am I pumping the well off? How can I optimize? There's different things, pump fillage being a big portion of that. And what is my pump displacement? Okay, with a dynamometer card, we ultimately calculate the displacement. Is what's going into the stock tanks, what's going into the production tanks, and what I'm measuring with dynamometer add up? That's an important point. Is the well pumped off? You can also calculate your pump intake pressure. Determine your pumping speed based on the accelerometer that's in the sensor, as well as conduct traveling valve and standing valve tests, which in the fundamentals section of this course, we're going to talk about testing traveling valves and standing valves, understanding what the valve tests look like, how to interpret them, as well as identifying basic card shapes for worn traveling valves and worn standing valves. Measuring the minimum and peak polish rod loads, measuring the minimum and peak rod loads. Okay, determining if the gearbox is overloaded, and then can I balance my pumping unit? We utilize the power clamps, but we can also utilize information input into the TWM software in order to balance the pumping unit. Crank information, weight information, distance from crank, gearbox information. And finally, is a gas separator necessary in this particular well? One of the things that we'll talk about is gas interference and introduce a little bit about gas lock. Some of the answers that you can get to these questions can ultimately help you increase the efficiency and optimize your well. So to basically introduce is, what is dynamometer? Well, when we look at a dynamometer card, the basic card that we plot is the surface card up on top. And what is the surface card? Well, the surface card is a plot of load over polish rod position. Whereas the downhole card, which is a calculated value, uses the wave equation to calculate what? Well, calculates the load over the pump rod position. And so these are some things that will be introduced in the fundamentals that we will talk about in great detail as we learn about the card shapes, peak polish rod or peak rod load, as well as minimum polish rod load. Okay. The important thing to remember is that the downhole card is always a calculated value utilizing the wave equation. Now, to introduce our first sensor, we're going to be talking about the 30K horseshoe load cell transducer. What is the horseshoe load cell transducer, and how is it different from the other sensors? Well, first of all, to add is that this is a very highly accurate transducer, because this particular transducer has the ability to be zeroed prior to placing it between the rod clamp and the carrier bar, which we'll talk about process of doing that here shortly. So very precise. Now, whenever you install it between the rod clamp and the carrier bar. Well, how do we get it there? Well, we're going to ultimately have to stack off the well in order to install that rod clamp so that it is load bearing and the strain gauges inside the equipment can measure the rod load. Okay. Now, TAM will calculate the velocity as well as the position of the polish rod by integrating the data in the acceleration signal versus time. One of the things is whenever you create the separation between the polish rod clamp and the carrier bar, as seen in the below picture, you'll need about 4 inches, so that way you can install the 30K load cell. Very accurate. It does require the well to be stacked out for the installation of the 30K load cell. It is a great piece of equipment that both comes in wired, as you see in the image, and has for a long time working with our wired well analyzer, as well as wireless. Now, this is one of those transducers that if you currently have a 30K wired load cell, you can send it in to us if you want to upgrade to wireless, and we can actually convert your 30K wired to wireless. Okay, 30K wireless uses the same strain gauges. Ultimately, now it has a board and has the ability to communicate with the wireless base station in TAM exclusively. Now, the next load cell that we'll talk about is the 50K load cell. Now, one of the things that I want to be sure to emphasize is that how do we get the measurement when we talk about utilizing load cells? Well, we're utilizing strain gauges with inside the Horseshoe load cell transducer to measure the actual rod load. And that's important. We're actually measuring rod load, the rod weight. Okay. And we're using the accelerometer and integrating it to get position. Now, with the 50K load cell transducer, what you'll notice here in the image on the right is that we actually have a permanent spool piece that is installed between the rod clamp and the carrier bar of the pumping unit so that we can easily and quickly install the HT50, commonly called, into the spool piece, and then utilize a hydraulic jack. We plug into the hydraulic jack and pump up the 50K load cell, and it's only changing the spacing of the well about 1/2 inch. And we'll install the spacer plate, as you can see here behind the 50K load cell. Once we install the spacer plate, we'll take the hydraulic pressure off the jack, allowing the pressure to collapse and ultimately the rod load to rest on those strain gauges. Now, some of the benefits between the 50K load cell and the 30K load cell is that ultimately when I install the 30K load cell, it changes the pump spacing by about 4 inches. Whereas the 50K load cell, it only changes it by about 1/4 inch. And the 50K load cell is easier to install. However, you do have to have this permanent piece of jewelry installed between the rod clamp and the carrier bar. Just some of the things to weigh. This spool piece and spool spacers are relatively cheap, easy to install on one. From a personal perspective, whenever I utilized Echometer equipment in the field that I was managing and over, I put it as a normal tool on each one of the artificial lift installations that we did for rod pump, that they all would possess the spool spacers and the spool piece. So that way we could easily and efficiently take 50K load cell measurements throughout the field without having to stack out the wells. A little bit of tying reality with the PowerPoint presentation there is something that we utilize on a daily basis, I would say. So very accurate, need to have spool spacers installed for the 50K load cell, and your technicians would carry a hydraulic jack with them. Now, this is an image of installing the 50K load cell, where you see that the 50K load cell transducer was installed here, and we utilized the hydraulic jack to create separation between the load cell and the jack. We utilized the spacer to install the spacer, and then we would take the pressure off of off of the jack and ultimately place it back on the load cell. So that way the load cell can measure load and then ultimately acceleration. Now, just like the 30K, the 50K can be converted to wireless. Comes in wireless, wired, and it's a pretty robust, good, very accurate tool because you have the ability, which we'll do in real time later, to zero the offset on the Horseshoe transducer prior to acquiring the data. Okay. Ultimately, derive a zero baseline before gathering the data. Now, there's an important point to this, and we're going to introduce this whenever we talk about the polish rod transducer more. But there is a point at which you want to measure real rod load, real rod weight, and the Horseshoe load cell transducers give you that ability. When we're identifying dynamometer cards that have ultimately lost pump action, there is no load exchange between the traveling valve and the standing valve, or one of the valves is holding load throughout the entire stroke. You really want to be able to measure that load with the transducer, which you're not measuring with the polish rod transducer. Okay, so keep that in mind as we introduce that. When we get into fundamentals, Gustavo is going to explain that in more detail. Now, the next sensor that we're going to talk about is what's called the polish rod transducer, or commonly referred to as PRT, or in the wireless version, WPRT. And what does this sensor do? Well, this sensor, as you can see from the image, it measures the changing diameter of the polish rod. Okay, so it records the change of the diameter of the polish rod during the pump stroke. As you can imagine, this is very, 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 very subtle change that's ultimately measured by very tiny strain, semiconductor strain gauges inside the sensor itself. Now, with this, there's also an accelerometer inside the sensor that we can integrate the data and tie in the wave equation to ultimately calculate this, or we can record the surface data and then calculate a good downhole pump card. Now, with this, we need to make sure that we have good rod information inside the software, and so that the PRT can accurately and with good belief in draw a surface and downhole dynamometer card. Okay, so the PRT is what? Well, it's not measuring real rod load. It's measuring the change in diameter of the polish rod and then ultimately extrapolating that into a surface card and then a downhole card. Still a very accurate, quick, easy way to acquire dynamometer data, but it is not measuring real rod load. And we're going to get into a little bit more of that. Now, this sensor is the WPRT. The WPRT obviously works with the wireless equipment, as you can see in the wireless base station. No wires, no coiled cables. Very common that most people that acquire data utilizing the wired PRT, you're very familiar with having to put the PRT up on the polish rod and then turn around and look at the computer in order to adjust it to the appropriate tightness. And as most of us know, the sun is always in the right position. We always have the computer screen at the right position, so that way we can ultimately see it. So we never have any issues with that, right? Well, wish that was reality, but that's just not the reality that was afforded to me anyway. So one of the nice things about utilizing the wireless polish rod transducer is that you can actually adjust the tightness of the particular sensor from the polish rod itself. And so as we go through the procedure, we'll ultimately introduce this more. But as you stop the pumping unit on the downstroke, install the polish rod transducer, TAM is open, you can push the install button in the middle of the screen here, and the install light above the button will actually flash red if the polish rod transducer is too tight, or green in blinks if you need to tighten it. Once the polish rod transducer is to the appropriate tightness, it will be a solid green light. So one of the, I guess, creature comforts of it is that you can adjust the polish rod transducer from the sensor without having to look back at the computer. I find that pretty handy and pretty nice. Now, with that being said, I introduced that the WHTs could be converted from wired to wireless. The polish rod transducers, on the other hand, cannot. Okay, so if you were going to buy a wireless polish rod transducer, that would be something that you would have to purchase new. We cannot convert the wired equipment. Now, one of the things that we do is the calculation utilized for the PRT measurement. And so we're measuring the variation of the minimum polish rod load, the MPRL, to the peak polish rod load, and it's measured accurately using a calibrated PRT. Okay, so the PRTs need to be calibrated, and that's something we do here at Echometer. Now, the program calculates pump dynamometer loads using the Wells rod description. I'm going to read that again. It utilizes the Wells rod description. So, with that being said, Echometer is a great tool, but you ultimately have to have good information inside the software in order to generate good results. Okay. Gustavo is going to talk more about what examples look like of incorrect rod description and how it can affect your dynamometer readings and calculating that downhole card. But it really is a garbage in, garbage out mentality. You have to have good information in the software to generate those good downhole cards. One other thing to that effect is that you need to make sure that you have a complete, whether you're utilizing a well view, whatever records you have are complete, so that way you can put them in the base well file. Yesterday, we learned how to create a base well file, okay? Create the well in the TAM software. Rod string information is very important for acquiring dynamometer data. Now, one of the things that I want to introduce here is that when utilizing the polish rod transducer, we're obviously measuring the difference between the surface load of the max polish rod or the peak polish rod load and the minimum polish rod load. Now, whenever we acquire this data, TAM is designed to shift the card, the downhole calculated card, to the zero load line, which is a term that Gustavo will introduce and talk about. It'll shift the traveling valve open point to the zero load line. And that is ultimately, and then we push the surface dynamometer data up with that adjustment. Now, that just sounded like words. Let me show you an image here. So the computed pump loads, when we run the PRT test, are ultimately placing the card below the zero load line, this being the zero load line. Now, what we do with the polish rod transducer is the program automatically sets the point at which the traveling valve opens and we discharge fluid into the tubing on zero. And we shift the surface loads up to adjust. Now, with that being said, what if we had no load? What if we lost pump load? What if we had a traveling valve stuck open? What if we had parted rods? These are all things that Gustavo is going to talk about. And what we ultimately see is we see what? No load transfer between the traveling valve and standing valve. And so you have a straight line. Well, if you plot that straight line on zero every time, you're not going to be able to determine exactly what's going on with the pump or the well when troubleshooting a well that has no pump load. So that may be a time, that is a time, where you would ultimately want to use the Horseshoe transducer to troubleshoot a well that has no load, something that we're going to talk about in detail more with Gustavo. Now, the wired PRTs have been around for many years, and they ultimately come in two different sizes. We sell them in 1.5 inches for most common practices here in the US, but also if you have polish rods that are bigger, we do have a 2-inch polish rod. I know sometimes, I think we've seen this in the Middle East where the polish rods are bigger because they require a larger carrier for that particular sensor. The larger polish rod transducer only comes in wired. Let me emphasize that. It only comes in wired. It does not come in wireless. Now, one of the things that's very important when we acquire dynamometer data, and the software does this, is we need to identify the individual strokes and then process the acceleration data to get velocity and position. So how do we get position? And you can see here how the software has picked one stroke. And then we analyze that one stroke, stroke by stroke by stroke. So how we determine the acceleration data is ultimately by integrating the raw acceleration data twice and then utilizing the wave equation to calculate the downhole pump. We're also measuring that raw load as the difference between the peak polish rod load and the minimum polish rod load, and then shifting the dynamometer card to the zero load line, which the traveling valve opens, and shifting the surface cards up. Okay, so there's a lot going on inside this little sensor. And I hope that this will ultimately introduce a lot of information so that you go through the fundamentals, you'll understand a little bit. Now, I'm going to dive into this side a little bit more in the procedures, so I'm not going to spend too much time on it. However, I do want you to know that it is very important when utilizing the HT, Horseshoe transducer, or the WHT, the wireless version, that you ultimately need to take a zero offset before putting any load on the transducer whatsoever. Like I said earlier, we want to start from a zero baseline, okay? If you're utilizing the wired equipment, you want to make sure that your cables are in good condition and they're ultimately pressed in, okay? You want to make sure that there's good communication if you're using the wireless equipment with the wireless base station. One thing to keep in mind with the wireless equipment is that it is line of sight. And so you want to make sure that there's good line of sight between the antennas on the sensors and the correlating base station. Now, with the PRT and the WPRT, installed to the correct tightness, which we're going to see the tightness meter in which we make sure that we get it in the green here a little bit later. One thing that's very important, though, is that you allow time for temperature stabilization. And what does that mean? Well, if you're carrying your PRT in your vehicle and it's a nice 75 degrees, and then you step outside 75 degrees Fahrenheit. I know a lot of you guys are using Celsius, but let's say 75 degrees Fahrenheit. Don't want to do that in Celsius, definitely wouldn't be. So if it's 75 degrees Fahrenheit in your vehicle and you step outside and it's 32 degrees Fahrenheit outside, what it's going to end up doing is the temperature, the transducer needs to stabilize so that you don't experience drift. Okay, so allow that transducer to stay out in the elements in which you're going to be conducting the test, so that way that you will not experience drift in the sensor. Okay. You need to make sure that the polish rod is clean. That's important. You know, one of the things that we're going to talk about, and I feel it's important to emphasize it in the procedures as well as this presentation, is that you want to install the polish rod transducer on raw polish rod. It's very common in the US that in some of our wells we run polish rod liners. Because the polish rod transducer measures the changing diameter of the polish rod, you don't want to install the polish rod transducer on a liner because there's no exchange in load and the sensor ultimately won't work. It needs to be installed on a raw polish rod. And same thing, if you install the PRT above the polish rod clamp, there's no transfer in load, so the sensor will not work. Make sure that you install it on raw polish rod. Now, with that being said, you need to make sure that the polish rod is clean, the raw section. So whether you use emery cloth or a good rag and some the contact cleaner, which you clean your microphone and your gun with, make sure that that polish rod is nice and clean. So that way, when you install it, you can confirm that you're getting good information. Okay. One of the things that you can do with the polish rod transducer is you can check for bending of the polish rod. The sensor will actually detect if the pumping unit is out of alignment. We'll talk a little bit about that in the fundamental section. And there's some things that you need for the polish rod transducers. You need to make sure that the polish rod diameter is verified in input in the sensor, so that way we can utilize it for the dynamometer measurement. Now, we get asked the question a lot as we travel and we teach these schools, well, the PRT doesn't measure real rod load. So is it accurate? I mean, it's great that it's safe and fast, but is it accurate? So we always like to throw this slide in here, comparing the measurement between the 50K, the 30K, as well as the PRT sensor. The PRT can be very accurate. You need to make sure that your information in the software is correct. One of the things I found myself utilizing is managing a team that would utilize Echometer equipment to optimize and troubleshoot wells in the field, is that all the technicians were outfitted with PRTs. And I kept a 50K load cell back at the office to where if we lost pump action on a well, we could go out and we could run the 50K load cell to determine exactly what the issue was. But if the well was pumping, if I was in routine operations and identifying, circumstances like what we'll talk about is full pump, gas interference, fluid pound, traveling valves, or standing valve slippage, the PRT was giving me great data, accurate and safe for my analysts as they went through the field. Okay, so red being the 50K, yellow being the PRT. As you can see how we plotted the traveling valve open spot on the zero load line, and then finally 30K being in blue. So the loads are very, very, very comparable in this particular example. Now, one of the things that we want to introduce, but we won't be talking much about it in the dynamometer section, is just power measurement. We also sell power measurement equipment that can help you install these 3 voltage sensors and the 2 current sensors to be used for what? Well, you can calculate your net gearbox torque. You can balance the pumping unit based on the different current on the upstroke and downstroke. So something to keep in mind, and I'm sure some of you guys have utilized this equipment. We won't go much into it, but it is available, just so you know. And utilizing TAM is something that is used, and it's something that we continue to develop and make sure that it's working well. Now, these are some of the TWM screens that some of you guys may be familiar with and you have seen as we're measuring the load on the upstroke and the downstroke. Okay, so something that we can talk more about, definitely. If you have questions about it, be sure to put them in the chat and we'll be happy to answer them offline. Now, one of the things that we do as well is we also have the wireless version of the power probes. As you can see from the top image here, the wireless version, you can connect inside the panel, as you saw with the wired power probes, but you also have the ability to install a fixed power adapter. A lot of companies don't want their technicians inside the panel box and exposed to live power. And so you can have a certified electrician go and install the fixed power adapter to the side of the panel box. So it's simply, you just take your power probe head, you screw it into the fixed power adapter, and you can acquire that power data without ever subjecting yourself or any of your field personnel to live power. Now, with that being said, one of the benefits of utilizing the wireless equipment is the simultaneous acquisition. And so as you can see demonstrated here with the fixed power adapter and the power probes, as well as the remote fire gas gun, which we talked about yesterday, the wireless pressure transducer and the PRT, you have the ability to acquire all this data simultaneously. So we can record power, we can record dyno while acquiring power and pressure, recording the tubing pressure, as well as shoot a fluid level. And you can see from the TAM image here we are shooting a fluid level while recording a dynamometer. So it's from an efficiency standpoint, it really makes it quite nice, not having to trip over cables as well as acquiring things simultaneously. Now, with that being said, what I'm going to do is I'm going to jump into the procedures on how do we acquire data with the polish rod transducer. The steps of how to acquire data with the polish rod transducer are very easy. Okay. Step 1, just exactly like setting up the gun, as we talked about in yesterday's fluid level training, is that you've got to make connection to the base station. So you're going to plug in your USB cable, which we had talked about yesterday as a USB-A connection to a Thunderbolt or printer connection to the back of the base station, and turn on your laptop. Pretty common sense. We're going to log into our Windows because TAM software has the ability to be downloaded on a Windows operating system. Okay. And we're going to start the TAM software, which commonly utilizes the icon that you can see on the bottom of the screen, the gray pumping unit with black letters that say TAM. Second, we're going to go up and we're going to pick a well. This is all looking familiar. Okay, so you follow the same steps regardless of the test that you'll conduct. So let's go to pick well in the top left. We're going to go and pick the appropriate well that we want to test. Except this time, we're going to click on the Dynamometer module, as you can see here on the left, rather than the liquid level module, which we went through yesterday. Now, when you're connecting your wireless polish rod transducer, you're going to first turn the sensor on. Okay. You're going to go to the top left and select Setup Hardware. And if this is a new pairing, you have not paired the sensor to your wireless base station, whenever you click on Setup Hardware and click Discover Sensors, you will have to pair the individual sensors. So once by clicking Pair, you will be able to drag the sensor over to a friendly sensor, as you can see in this below image, and then you will not have to pair that sensor again. Once the sensors are friendly to the base station, when you turn the sensor on and plug the base station in and start TAM, it should automatically come over. Okay, so the pairing, just like you're pairing your cell phone to a Bluetooth in your vehicle, you just have to do it once, and then it remembers the sensor. Very similar with the wireless PRT as well as the HT that we'll talk about. Now, with the PRT, there's not you don't have to get a zero offset on it that we'll talk about with the HT. Okay. However, with all sensors, you do want to make sure that the sensor is picked up at the top of the toolbar. If the sensor that you're utilizing is not present, you're going to click on Pick a Sensor, go down and select the appropriate sensor that you want to use. Okay. Most of the time it comes over automatically, but if it's not present, go up, pick a sensor, and go to that particular sensor. Now, this is important. Before we install the polish rod transducer, we want to stop the pumping unit near the bottom of the downstroke so that we can install this polish rod transducer on the raw polish rod. Okay, so want to turn off the pumping unit and set the brake. Now, one of the things that you'll notice with your polish rod transducer, or if you plan on getting one once you receive it, is that the polish rod transducer has a half moon cut in the carriage of the polish rod transducer. You want to make sure that you center that half moon cut on the polish rod. If you do not center that half moon cut on the polish rod, it can cause load drift and will ultimately give you incorrect data. So you always want to make sure that you center that in the half moon cut. Now, with the wired equipment, you want to make sure that that patent label is always facing up. The direction of install does matter. You want to make sure that it is facing the right direction. With the wireless equipment, if the buttons, the power, the acquire, as well as the buttons, if they're facing the right direction, facing up, then the particular sensor is facing the right direction. Okay. Now, step 4 is only lightly tighten the polish rod transducer. So get it up there, adjust it just a little bit, because we will do a little bit more finite tightening in just momentarily. Now, as you can see from this picture, I've installed the polish rod transducer on the portion of polish rod that I would consider the raw portion of the polish rod. Down here, we have a polish rod liner. I will not install it on the polish rod liner, but I will install it on the raw portion of the polish rod. Okay, this is important. At least 6 inches from a load-bearing clamp. My clamp is up here out of the view of the image, and so I'm well below 6 inches from that clamp. If you have a carrier bar that is coming down and almost hitting the top of the stuffing box, be careful not to smash your wireless polish rod transducer, because it has happened before. So make sure you have plenty of raw polish rod exposed in order to tie in this small incremental sensor. Now, when we install the polish rod on the well, we're going to place it on the polish rod, and then we can press the install button. As I was alluding to earlier, some of the difference between the wireless polish rod transducer and the wired. When we hit install, we'll see if the switch blinks green, then we need to tighten it until it turns solid green. However, if it blinks red, if it turns red, then we'll loosen it in order to make sure that that light is green. Now, one of the things that you can do is, once you get it to the appropriate tightness, and you can do it from the computer screen or you can do it from the sensor. Everyone has their preference, because this tightness, this green, yellow, and red bar will still display once you hit the acquire button on the sensor. So once you get it to the appropriate tightness, you can continue the test and ultimately continue the dynamometer test by clicking continue at the top of the screen. Now, if you say, I don't really want to start it from the sensor, I've always done it from the computer, you can still do that. Go over, you'll install the polish rod transducer on the polish rod, and then if you click Start New Test up at the top right of the screen, this gauge will pop up and will allow you to install it to the appropriate tightness, and then you can click Continue to start the test. So continue starts the recording. We're going to release the brake and start the pumping unit. And then we're going to be able to generate real-time dyno cards at the time of the acquisition. Now, it's very common that about 2 strokes will pass before you start utilizing real-time dyno cards. So if you're running the dynamometer data and the data doesn't instantly pop up, it's okay. Give it 2 strokes before the data will pop up in real time. After you've acquired your required dynamometer information, okay, what you'll do is you'll click the stop button, and then you've acquired your dynamometer data. Whenever you decide that you want to report the information, you can go up and click on Report above the dynamometer card displayed, and you will be able to display a PDF report and submit that to the engineering staff, your clients, or if it's for your own personal use. Now, one thing to keep in mind is that the reports generated will show 1 stroke. So you see here, stroke 12 of 12, 1 stroke of data, and you can go through and you can pick different strokes and generate reports. Okay, so it's representative of 1 stroke of data during the acquired time frame. Now, removing the dynamometer sensor, you're going to go in reverse. We're going to stop the pumping unit near the bottom of the stroke. We've already stopped the test. You want to make sure you stop the test before removing the sensor. You're going to make sure that you remove the sensor, okay, turn off the equipment, and then start the pumping unit back up and leave the well in the condition that you found it. So that is the procedure on how to utilize the PRT. Now, the next sensor that we'll be going to is the Horseshoe load cell transducer. And with the Horseshoe load cell transducer, it is a little bit different than utilizing the polish rod transducer. Because one of the things that I had mentioned earlier is that with the polish rod transducer, we can simply walk up and install it on the raw portion of polish rod. Whereas with the Horseshoe transducer, we actually have to stack out the well. Okay. Now, one of the things that I want to emphasize is that me stacking out the well in this procedure, it may be different for what your wells require. Okay. There are some stuffing boxes that you can't put the weight of the rod string on. So be sure that however you create the separation between the carrier wire and the rod clamp, that you do it in a safe manner that ultimately is recommended by your company. You want to make sure that it follows your company's safety guidelines and protocols. Okay. Number 1, from a safety perspective, is we're going to survey the location in the pumping system to make sure there aren't any unusual or potentially unsafe conditions. If you have a wrist pin that is popping or a saddle bearing that is popping, and it's something that's new, it may be a time that you don't really want to be stacking out the well and put yourself in harm's way. Now, we talked about the 30K load cell and the advantages of it. And as you can see in this particular image, the load cell is mounted between the rod clamp and the carrier bar. Okay, we talked about high accuracy. We talked about zeroing the load cell. Now, before we get to this point right here, to where the load cell and the strain gauges have the weight of the rod string on it, we should have already conducted the zero offset, which is something that we're going to do in this procedure. And then once we finish, we'll do it in TAM software as an example. So very similar, the same setup as you do with any sensors. Going to plug in the USB cable, going to start the TAM software and pick a well, select dynamometer, and then we're going to connect the sensors utilizing the same steps and procedure that we use with the wireless PRT. Now, we're going to do this in just a little bit, okay? But you're going to turn on the sensor, select hardware. If the sensor hasn't been previously paired, you're going to click Discover Sensor, pair that sensor, and then the difference between the PRT and the Horseshoe load cell is that now with the Horseshoe load cell setting on, whether it's the back of your truck or the pumping unit base with no load on it, we're going to go up and we're going to click Perform Offset. Okay. The next page will actually demonstrate that better. So once we've paired the sensor, we can go up and pick a sensor if it's not present. Okay. Once we pick the appropriate sensor, as you can see represented here, the WHT140 is selected in the top of the toolbar as well as the sensor that I'm utilizing. Okay. Now, it's very important, like I've said multiple times, that we get a 0 offset on this particular sensor. So once we select the sensor, we have the ability from the Setup Hardware menu to click Perform Offset. And then once the load stabilizes, we're going to click Use Shown Value after the load is stabilized, and that locks in that 0. So you're going to 0 the Horseshoe transducer. You're not going to 0 the polish rod transducer. Let's walk through these steps. Now, in this particular example, what I have is I have a Horseshoe load cell transducer that is sitting on my countertop across the way. And I've just turned on the sensor, so that way my base station can discover it. And so if I go up to Setup Hardware here at the top left on the screen and select Setup Hardware, this particular sensor is not appearing. Well, for one thing, it's because it's a new sensor and I haven't paired it with my base station. So I'm going to navigate down to Discover Sensors, in which WHT2195, being the serial number, now has appeared, and I'm going to have to pair that particular sensor by clicking on Pair. Once I pull the sensor over to my friendly sensors, from now on, each time I turn on the sensor and I'm connected to the base station, it will go to the friendly side. Okay, so I won't have to go through the pairing process again. Now, one second. All right. My sensor decided to turn off on me. So now that we have the sensor paired, and it is a friendly, okay, now I've got the ability to take a 0 offset on this particular sensor with no load on it. And so what I'm going to do is I'm going to go over to Perform Offset. There's no load on the sensor, and I'm going to click Perform Offset. Now you can see in this particular offset, the base in my office is we've got about a 30-pound offset that will be our new base to lock in. So once I'm satisfied with the offset, I'm going to go up and I'm going to click on Use Shown Value. And that's going to lock in that 0 offset. And now I can utilize the sensor. Okay. Now there's different positions in TAM in different places in which you can take this 0 offset. You can either do it from the Setup Hardware menu when you actually connect the sensor. Or let's say that you don't want to go through Setup Hardware. If you go up to the top of the screen and you click on the individual sensor, that will also display the Perform Offset. Now, one of the things that I need to mention here is just exactly like we were talking with the wireless equipment yesterday in the fluid level section, is that the coefficients for the wireless equipment will automatically come over and will be stored whenever you turn on the sensor. Now, if you have wired equipment, you will have to manually go in there and enter in the individual coefficients. If you send in your sensor to be worked on, to be calibrated back to Echometer headquarters, when we send it back to you, you will have new coefficients. And you need to make sure if you have the wired equipment that you go in and you change those coefficients prior to using the sensor. Okay. So that is how you go through and you take an offset with your HT sensor. Now, back to the presentation. So once we acquire the offset, very similar to how we take with the PRT, is we're going to stop the pumping unit carefully near the bottom of the downstroke. Okay, we're going to stop the pumping unit. And now we're going to go through the process of installing the WHT, the wireless Horseshoe transducer, on the wellhead. You can see Mr. Ken Skinner there, Echometer legend, ready to install the Horseshoe load cell. So one of the things that we need to do on this particular well is we're going to create separation and stack out the pumping unit, creating space, so that way we can put the 30K load cell between the rod clamp and the carrier bar. So what we're going to do is we're going to install a rod clamp on the raw portion of the polish rod. So that way we can utilize a suitcase or a stack-off tool in order to create separation between the carrier bar and the rod clamp. Okay. You want to make sure that you position your polish rod clamp to where you can create enough distance to be able to install your 4-inch load cell. It is very important that you want to make sure that you remove any accessories or tools that are between the load clamp or between the rod clamp that you installed and the top of the stuffing box. Any polish rod lubricators you want to remove. Also, if you're using a dual pack stuffing box, you want to make sure that you run up the stack off nuts before you stack it off as to not collapse your packing. We're going to install the stack off tool, or commonly referred to as a suitcase. And in this particular one, there's not a chain. I would recommend utilizing one that has a chain, so that way you can secure it to the wellhead. And so if it were to come off, it would be stuck on the wellhead. Okay, so make sure that you keep safety as a top consideration when stacking out a well. With the stack off tool installed, we're going to release the brake, momentarily turn on the pumping unit, stacking off the well, creating separation between the polish rod clamp and the carrier bar. We're going to turn off the pumping unit and then set the brake. Now, this is a well in which you can see that the polish rod clamp is resting on top of the suitcase. Okay. You can see the separation that is now created between the rod clamp and the carrier bar. This particular well we test quite often, and so you can also see that we have a 50K spool spacer in here as well. Now, obvious reasons, never position your hand between the carrier bar and the rod clamp. The suitcase is holding the weight of the rod string. You never want to put your hand inside of a pinch point where you could ultimately lose a digit. Now, once we install the load cell, you're going to make sure that you install the load pin, the safety pin, as you can see in the below image. So that way, if there was a stack out event when conducting the test, the horseshoe load cell transducer would not fall out of the front of the pumping unit. So the safety pin is paramount, important. Make sure that you install the safety pin when utilizing the horseshoe load cell transducer. Now, once you've installed the horseshoe load cell transducer, okay, and the area is clear, you're going to carefully release the brake, transferring the rod load back onto the load cell into the carrier bar. Now the load cell is measuring the rod load. Okay, we'll remove the stack off tool and place it off to the side. We can go ahead and go up to the top of TAM at this point and click Start a New Test. You don't have the ability to start the acquisition from the sensor itself. You will be starting this from the computer. So we'll click Start a New Test. We'll turn on the pumping unit, acquire our data, exactly like we do with the wireless polish rod transducer, generating a surface card as well as a downhole card. And then once we've acquired the number of strokes that we feel is to have a successful analysis, then what we'll do is we'll go up and we'll click on the stop button, stopping the test. And as we talked about last time, from there, you have the ability to go in and create a PDF report and actually create that PDF report and submit it to the engineering staff or whomever you would like to send it to. Okay. Now, an important portion is after the completion of the dynamometer is done, okay, we're going to talk about removing the horseshoe load cell transducer. So once again, we're going to stop the pumping unit and turn off the power. We're going to reinstall the stack off tool. As you can see, Mr. Ken here installing the stack off tool, as well as utilizing the chain, making sure that we have it chained in position. We're going to release the brake and momentarily turn on the pumping unit, allowing the stack off tool to hold the weight of the rod string and creating separation between the carrier bar and the rod clamp. I'm going to turn off the motor and set the brake. Now, once the load cell you have separation between the carrier bar and the rod clamp, you can ultimately remove the safety pin and remove the 30K load cell from between the carrier bar and the rod clamp. Okay. After this, we're going to release the brake, allowing the polish rod clamp to now have the load once again. Once the stack off tool is removed, we're going to install all the implements and all the accessories that were on before. Lubricator, anything that was on the wellhead before we actually decided to take the measurement. Now, I'm going to verify that all valves, piping, and everything is returned the way that it was. I don't want you waking up in the middle of the night thinking, did I open that valve? Because I know we all do that at times. Okay. Position everything back the way that it was and ultimately return the well to production, coordinating with the well tender, operator, pumper, whoever it is, just letting them know that, hey, well's back in production. Now, with that being said, okay, we have gone for about an hour now. We've covered the introduction to the website. We've covered what the individual sensors are. Okay, we have gone through how to acquire a zero offset.
Welcome back. On the next portion of the presentation, we'll be talking about dynamometer analysis fundamentals. So basically, we'll be reviewing information that has been recorded with Echometer equipment, both PRT and Horseshoe load cell sensors, Justin covered in the previous session. So one of the things that we have to focus on when we're analyzing dyno cards is first understanding what a dyno card means and what is that graph, what kind of information is providing. And basically, a dynamometer card is one of the primary tools that you will have available to analyze a rod pump system performance. Before I go any further, I wanted to remind you that our contact information, you can follow us on LinkedIn. There's usually some information posted there. Keep you up to date with what's going on around here. Also, if you have any question, inquiry, need any help, here are Justin's and my contact information. So that's our email. We all go by the name at echometer.com. Well, let's continue talking about dynamometer data. When it's referred to dynamometer analysis, there is a bunch of information that we can review. Unfortunately, most people, I wouldn't say most people, but still a lot of people are used to look at dynamometer data just to look at the dyno card shape. And they try to understand everything that's going on in the system just by analyzing a dynamometer card shape. When actually, you have a lot more information. What you see on the left screen there, if you can see that, is a portion of the dynamometer report where we can understand multiple points of the system where not only how the pump is pumping, but also we can understand how the rods are loaded, about the pumping unit itself. How is the structural balance? How much torque we have in the gearbox. So we have a pumping unit that is designed to lift some weight. So structural capacity is one thing that we need to focus on. We want to make sure we don't overload the pumping unit. And we can also understand downhole conditions. Is the pump being affected for gas interference? Am I overpumping the well having a pumped off condition? Having an indication and even fluid level height based on dynamometer card shapes or height. And we want to cover basis of understanding how dynamometer card shape works. Gearbox torque is another portion of the report that you can review if you input the information, the necessary information in the software, like pumping unit, counterweights, crank information. The software will have normally enough information to understand about gearbox balance, loading, but also if you have available a motor, an electrical motor, and you have a power probe, you could simultaneously record power data. We don't have enough time to talk about power, but it can be a simultaneous acquisition when you're acquiring dynamometer data. So with that, understanding the operation of a socket rod pump is what determines the car shape or the car characteristics. When you're acquiring data at the well, you normally come with more than just a dynamometer sensor. So when you come with Echometer technology to a well, you shoot a fluid level, you acquire dynamometer data, and what's important here is you put those two pieces of information together, and that actually should complement to each other. When you shoot a fluid level, you have an expectation of how the dynamometer car shape should look like, and vice versa. When you get a dyno car, if you have a full pump, you're not expecting to see a fluid level at the pump. If you see a pumped off well, you're expecting to see a fluid level very close to the pump intake. So on top of that, I will show about some reference lines, being that a FO, and that stands for fluid loads, that should make sense about the dyno car height and a reference line from the fluid level. So let's start with understanding about the relationship between a fluid level and a dynamometer car. And yes, those are two separate measurements, but they should complement each other. And the dynamometer car height that we have in the well, it corresponds to some pump submergency. So the lower the pump submergency, the taller, let's say, the dyno car shape is, or dyno car is. And the opposite, the higher the pump submergency, the higher the fluid level in the well, then the shallow, the thinnest, or the pumping unit becomes, so it gets flatter and flatter, smaller and smaller as the fluid level goes up. And why that happened? Well, it all has to do with pressure. How much help is the well providing to the pump? So let's convert this into a pressure profile. So we have a well, and let's say this is the well depth, this is pressure. And one of the things that is important for me to pass a message on is how pressure profile work in the well and how much help we need from the pump. So why are we spending money on installing an artificial lift system? Well, because the reservoir itself doesn't have enough energy. So we have to provide some sort of energy downhole so we can lift the wells up to surface, because the reservoir energy is not enough to produce the well, not in economic quantities. So with that, if we go and run a gauge down the casing, if we could do that, then we have a casing head pressure, and let's say that's about 30 psi, and we have a gas column. When we get to the top of the liquid level, let's assume first we have a high liquid level in this well. And we go from that point on to the pump with a casing gradient, basically an oil gradient to the pump intake, resulting in this example of 2200 psi. You can extrapolate that to the bottom hole and calculate the producing bottom hole pressure, but we're going to focus on the pump. So inside the tubing, if we look at the pressure gradient inside the tubing, let's say we have a tubing head pressure of 50 psi, and then we go down the tubing with a tubing fluid gradient, which is a mixture of oil and water. And let's keep the gas out of the equation for now. So we have a tubing gradient, and we result in a pump discharge pressure, which is the pressure above the traveling valve, resulting from the hydrostatic column in the tubing plus the tubing pressure of 2500 psi. So this well, in order to flow, it needs 2500 psi to lift the fluids, the tubing height from the true vertical depth of the pump, and overcome the line pressure. So we have a tubing line pressure, surface pressure that we have to overcome to be able to flow to whatever the delivery point is, your tank, your battery, your separator. Meaning this, we need 2500 psi, the pump intake pressure is 2200 psi. So the pump needs to provide the differential pressure. So the extra needed pressure in this case will be 300 psi. So the pump is actually providing 300 psi of extra pressure. If you go and shoot a fluid level and determine bottom hole pressure, you see you have high pump submergency, probably and very likely. Your recommendation will be, I'm going to speed up this well. Depending on the type of well it is, you can increase the pumping speed, the hertz, the RPMs, do something about decreasing the column height so you can decrease the bottom hole pressure. So you take actions, the fluid level is now lower. So what happened there? Now you have casing head pressure, now a higher gas column, that's very light, then oil column that results now in a lower pump intake pressure as the fluid level goes down. So we have 1100 psi, but still inside the tubing, we have the same gas liquid oil composition. So let's say we need 25, we still need 2500 psi. Now the pump is receiving less help from the well and still have to provide a 2500 psi, meaning that we have to pump with, this pump has to provide a 1400 psi additional pressure to the system. So it's receiving 1100 psi, delivering 2500 psi. So the pump work is basically increasing the fluid pressure by 1400 psi in the system. And that goes on as the fluid level goes down until you're basically pumped off. So when that happens, lower fluid level, lower pump submergency, meaning less help from the well to the pump. So the pump is basically taking low pressure fluid now, compressing that mixture up to 2500 psi, delivering that into the tubing. So the pump is providing an additional 2200 psi of fluid pressure there. So as the fluid level goes down, the pump is required to provide more and more pressure. So that's the pump work. Basically, the difference between the pump discharge and the pump intake is what the pump is providing. Now, we can convert this PSI into load. How? Well, the pump has a plunger and the pressure is applied on the plunger area. So we can always convert that pound square inch times the square inch of the plunger and the pump and convert that into load. And that's what we have in a dynamometer card. So the vertical axis in the dyno card will be load. So we can convert the pump differential pressure into load. So the higher the fluid level, the lower the pump work because we have more help from the well, being a flatter dyno card. And as the fluid level goes down and down, then we have a higher and higher dyno card, and then it will reach a maximum. And the maximum, the theoretical maximum, is what we call an FO max, meaning the maximum fluid loads the pump can live. And basically, that's when the pump intake is 0, when the fluid level is at the pump. Kind of technically impossible if you have some gas because you may have some casing head pressure. But the lowest tubing intake pressure and the same pump discharge pressure will give you the maximum fluid loads. And if you think on that, the pump is actually providing the additional help to lift the fluids from the fluid level to surface. How that works? Well, imagine you don't have any rods or pump in this well and you have only tubing. If there is nothing blocking the tubing intake or providing any assistance, the same reservoir pressure that is lifting the fluids up to this fluid level height inside the tubing, it would lift the fluid to this point as well. So it would be equalized by communication at the bottom of the tubing. So even without any pump, the tubing will be full up to the fluid level height. Then if you install the pump, then the additional help would be lifting the fluid from the fluid level top actually to surface. That's kind of another way to see what the pump is doing for the system. So another thing that I like to highlight in our classes is kind of changing their mind and the mind of people out in the field just collecting data. So the company is providing you with a truck and a set of equipment and you're going out, but actually your goal is not just going there, install something, measure whatever, send it to someone who understands what's going on. I think the role of a artificial lift tech should be going beyond that point. The goal should be answer, what is the well doing? How is my well performing? What kind of problems I have? So if you're going to a well, you are the best person to understand what's going on. You're there, you're feeling the well, you're listening what's going on, you're experiencing, you're looking at gauges, feeling pressures, temperatures, flow. So you are right there at the action point. Then you will be a person who don't only collect the data, but also analyze the data at the well. As you are collecting data, you're looking at the well shape, you're looking at the gauges, what the well's making, is the well producing or not? How is it running? Is there any additional noise, vibration, things that may be affecting the system as a whole? And then when you analyze the data at the well, you will be in a better shape to recommend actions to fix problems you may find during the data collection and interpretation. So you should be the person recommending actions to fix problems in the company. At least talking, if you're a field personnel, you don't have the call, then talk to the engineer or whomever is taking the optimizations decisions and talk about what you saw in the well. Use your annotation box. There is a comment box in the software where you can record what you recommend or what you're experiencing at the well that may help to make the final decision on how to analyze the work, how to tackle this well, how to fix the problems. Then when the problems are, when the changes are completed, that has been recommended and completed now you got to go back to the well, get new data, understand if those changes worked as planned. Of course, you have to wait for that well to be stabilized. You don't have, you can't make a change today and go in the afternoon and go tomorrow morning. Allow some time for the well to stabilize, pump in a normal condition, then go and measure and see if the problems has been fixed, if the optimization has been successful or not. Then you have to notice if the well performance has changed. Did it work or not? And follow up on those recommendations. You got to learn if what you're doing is going the right way or not. Should you keep doing that for the next wells having similar conditions in your field? So learn about the results. Basically, it doesn't matter if they are good or bad, you will always have learning experience once you try something. And then by doing that, your role in the company will change from just being a data collector, just someone that goes with equipment and gather data, to a more knowledgeable technician out in the field, someone who analyzes the problems and solve the problems. I think that's one of the beauties of this technology. Empowers you, allows you to perform well optimization from A to Z with not many other tools. You have most of what you require out in the field with this equipment. A common question is what type of data we need. And just actually yesterday we had the similar question for the fluid level. Now let's talk about what is critical information for dynamometer data. Well, I would say let's start with the most critical one, which is the rod string details. So you need the rod type, the taper length and diameter of that taper. You need the polish rod diameter, especially if you are measuring with a PRT, the polish rod transducer, because it's connected to a polish rod and we'll be looking at deformation on the polish rod, and the plunger diameter. That's critical. There are many calculations and the car shape will be affected if you change the plunger diameter, because there is a calculation that is converting the surface card into a pump card. So plunger diameter plays a role there, especially if you're doing a PRT calculation. Another things you can input and you should know where the pump intake is at. And then if you have information about the fluid, even better to calculate better gradients. And you can enter the fluid gravity, so being all API, water specific gravity, and so on. Production rates, so you can compare the production rate to what the pump is calculating. Look at making better fine tunes on your adjusted pump displacement calculation. We will discuss a little bit more about that in the next slides about when we're looking at some dyno cards about how the software calculates pump performance, pump displacement. Surface data, you should be able to measure the tubing head pressure. That's one of the factors that affect the car shape. So inputting the software, the tubing head pressure is important. If you have a pumping unit information, it's important to enter that. You will allow the software to calculate pumping unit structural capacity loading, gearbox loading, and recommend you how to balance the pumping unit by moving the counterweights and things like that. So information there, it would be the pumping unit type, geometry, the API nomenclature, basically. How is the pump rotating? If it's a pumping unit like a conventional unit can rotate either clockwise and counterclockwise, you can input that information. And if it's an electrical motor, you can always input the electrical motor information. Most basic information, recapping, rod string information, plunger size, pump intake, and that would be at least what you have to input in the software aside tubing casing information. Now, dynamometer cards. So when we talk about dyno cars, most of the time people are referring to the pump car. So what is the difference? There are actually two pump cars. There is a sensor that is installed at the surface at the polish rod, measuring the polish rod load and the polish rod position. How many inches is that polish rod moving up and down? And that load fluctuating up and down and the movement of the polish rod is what generates the surface car. So we measure the surface car with any of the sensors. So we have in the vertical axis, we have the load and the position on the horizontal, which will result in a surface car. Usually hard to interpret. The deeper the well, the harder to interpret. The faster the well, the harder to interpret because the dyno car shape fluctuates a lot based on the well condition and how are we operating the well. But most people focus on the pump car. So, but what is the pump car? We are not installing a downhole sensor, but we can see a pump car. So basically, what we're doing is we get the surface car, we apply some math, kind of complicated math to this surface car's wave equation to convert the surface car into a pump car, which is the equivalent, like if we would be able to install a load tail right on top of the plunger. So like on the valve rod, if we would be able to measure the loads and the position of that plunger, that is the representation of the pump car. There will be factors that affect the pump car shape, and hopefully we are accounting for most of those. And there is not much residual friction and things that may be affecting the pump car shape. So most of the time we have a decent dyno car shape available, and with Echometer equipment, more reliable because we have sampling speed that are much higher than conventional controllers. So we have more details in a pump car coming from an Echometer dynamometer sensor. So we'll be focusing on interpreting most of the dyno car shape at the pump. Quickly, kind of a refresher, any pump that you know, at least the most basic rod pump will have some components. So you have a traveling and a standing valve. And what I'd like to highlight here is pressures that we'll be talking about. We have something we call a pump discharge pressure, and that's actually above the traveling valve. That's what we call a PDP, a pump discharge pressure. That's a pressure above the traveling valve. And we have the pressure below the standing valve. So that would be the pump intake pressure, which is actually a result of the casing head pressure, the height of the fluid level that results in the pump intake pressure. The difference between discharge and intake is what the pump is providing. So in between those, we have the pump chamber. So pump discharge pressure will be fairly stable during the cycle because we have a tubing full of fluid resulting in the pump discharge pressure. The pump intake pressure is also very stable during the cycle because we have a fluid level that is not fluctuating much during the stroke. So we have the same casing pressure, about the same tubing fluid, casing fluid level. So we have a very similar pump intake pressure along the stroke. And what's going to be changing a lot will be the pressure inside the chamber, as we are compressing the fluids above the discharge pressure and allowing another portion of the stroke, allowing the standing valve to open and filling up with the liquids from the well. We'll be talking about how that pressure fluctuation dictates the car shape. So basically, that's talking about the pump mechanism. We have basically two check valves, traveling and standing valve, basically a ball and seat assembly. It's a check valve that only allows the flow in one direction, up to surface. So the valve opening is controlled by just the difference in pressure. So it's just the differential pressure in the pump. We need to have more pressure above, if you have more pressure above than below, the valve is closed. But if you have more pressure below the valve than above, then the valve is open. So this is just differential pressure. It's controlled by pressure. There is no other mechanism playing there, but pressure and well, when there's no pressure differential, then gravity puts the ball on the seat. The pressure inside the barrel is a function of the travel of that plunger and the compressibility, and this is a key word here, the compressibility of the fluids in the barrel. So what's in the barrel once the upstroke happens? At the end of the upstroke, when the plunger is on top, what is in the barrel? Is that only liquid? Is that liquid and gas? Is that mainly gas? So more compressibility or less will dictate the car shape. We said already that the discharge pressure is the pressure at the bottom of the tubing, inside the tubing, and the intake pressure is actually the pressure outside of the tubing, below the standing valve, and that's controlled by the casing head pressure and the fluid column above the pump. Valve closing is controlled by gravity if there is no differential pressure, and viscous drag inside the cage, and it will avoid the flow back because this is again a check valve, but also differential pressure will play in there. So in any pumping cycle, we have these four components. So at the beginning of the upstroke, talking about the chamber, we have an expansion point. So when the plunger moves up, the chamber pressure decreases because the space is growing. Then that pressure goes below the intake pressure. So now having more pressure below the standing valve, that opens the standing valve. And that's what we call the all the intake cycle, when the plunger is moving all the way up and the standing valve remains open, allowing fluids, and hopefully just most liquid and gas, goes inside the chamber. Now, the beginning of the downstroke, we're now trying to compress that. And as you can notice in the picture, both traveling and standing valve are closed, at least at some point when the pressure equalizes. And now we're trying to compress the fluids inside the barrel. Compressing the fluids, at some point we will reach a pressure inside the barrel that exceeds the traveling valve. When that point is reached, then the traveling valve opens. And once the compression finishes, then we have the discharge cycle. This is discharge section of the cycle. And that should happen no matter what. If the pump is actually working, if you're pumping, that should be happening and along the stroke. So talking about how compressible are the fluids. If at the end of the upstroke, you have a pump that is completely full of liquid, there's no gas in there, you don't need much plunger movement to squeeze the fluid inside the chamber to increase the pressure dramatically. It's like liquids are almost uncompressible. So a slight movement of the plunger would result in a high pressure increase inside the chamber. And when we have that, we can convert that high pressure increase into a car shape. So at the beginning of the upstroke, and let's look at the dyno car shape. Every stroke, when we're analyzing a dyno car, starts at the lower left corner. We have that going up, could be just picking up the loads, and we can see at the beginning, we have a small plunger movement, and this is kind of exaggerating the movement, but we increase so that the pressure inside the chamber goes below the intake pressure, allowing the standing valve open, and that should remain like that along the upstroke. Then we finish the upstroke, still the pressure in the chamber is close to the intake pressure, slightly lower. And now we start the downstroke. What's going to happen with the pressure in the chamber is going to increase, but it has to increase above the 2500 psi in order to open the traveling valve. So as it's moved down, and we don't really need much movement, this is in a kind of a exaggerating the movement so we can see that plungers moving down until that plunger, the barrel pressure exceeds 2500 psi, then the traveling valve opens, and we have a pressure inside the chamber that is much higher than the standing valve, so the standing valve remains closed. So across the traveling valve, we lost the differential pressure, we lost the loads that the polish rod were picking. So when the plunger moves down, increases the pressure, equalizing here, even exceeding by some psi, open the traveling valve. The pressures, the loads drop, and that should remain like that during the whole downstroke. So in an ideal world, a rectangular car shape would be resulting from a full pump. We have close to the rectangular car shape, and this is one example of that. So this is a full pump in a well. We pick the loads and the plunger takes off, move upstroke, gets to the end of the upstroke. From the higher right corner to the lower corner, both valves are closed. We're compressing until we reach the pressure to open the traveling valve, and this corner will be called the traveling valve opening point, and that traveling valve should remain open along the stroke. Again, picking the loads, we're just picking loads, both valves are closed. standing valve opens right here. The traveling valve continues going up till the end of the upstroke. Then the standing valve close. We start compressing until we reach that point when the traveling valve opens, and that happens during the downstroke. So it's just a matter of how the chamber pressure change. The more compressible, the car shape will be different, and that's what we'll be discussing next. So this is a regular car shape. This is a full pump, and that's kind of a rectangular shape, but the car shape will be affected by the tubing being anchored or not. So if you have some tubing movement, we could have a full pump, still full, but will be slant to the right. The result of that is, well, we are affecting the effective plunger travel. And you can see here an MPT and an EPT. I'm going to explain what that is. So the MPT is the maximum plunger travel. That's the maximum number of inches, the total number of inches the plunger moves up and down. Remember, a dyno car is load in the vertical axis and inches or position in the horizontal axis. So plunger moves up and down all the way, and that's what we call the maximum plunger travel. But the fluids only move from the chamber to the tubing across the traveling valve when the traveling valve opens. And in this case, the traveling valve opens later. That's affecting, that's what we call, after the traveling valve points, what we call the effective plunger travel. So not all the stroke is used to displace fluid to surface. Only when the traveling valve opens, then the fluid moves from the chamber across the traveling valve into the tubing. So the difference between maximum and effective plunger travel. So remembering that, we have to consider that car height now will have an indication of how much help from the well, meaning how much submergency we have in this well. If the dyno car height is close to the FO max line, and again, the FO max will be the maximum fluid loads, assuming there is no help from the well, meaning there is no pump submergency, or when you have a lot of pump submergency, the difference between the FO max and the car height, that will be the additional help from the well. So we'll be discussing about that. Basically, let's use this dyno car as an example, and we could say that this pump submergency here is the difference between the height of the car and the FO max line. And we will have this reference line, the FO max and FO from fluid level in the software. I will show that. So what is this? Well, the pump is actually, I mentioned before, the pump is lifting the fluid from here to surface. So that section is actually the car height. That gives you another way to see quickly if you have pump submergency or not in this well, based on the dyno car shape prior you shoot a fluid level, or matching on the fluid level information. This is an example here, a well that has a maximum plunger travel of 267. And we see a difference in height from the FO max to the upstroke load. So we can tell there is a good amount of pump submergency in this well. We can also see the pump car slant to the right. We see a KT line, which is the tubing stretch line. And there is more slant to the right in this dyno car, which indicates some traveling valve leakage or some pump wear. But I think the diagnosis here will be an anchored tubing and some traveling valve leakage, and we'll see an example of that in the example section later today. Now, there are conditions or problems downhole that will make the pump not to be full of fluid, and that goes in detrimental of the system efficiency. We are installing a pumping unit, rods, pump, to make the plunger move, but the pump is not full of liquid. We're doing that to displace liquid. And if the chamber is not full of liquid, we are losing system efficiency because we're spending a lot of energy to move a plunger, and the plunger is not displacing fluids to surface. So there are reasons why the pump could not be full of liquid. And if the pump is not full of liquid, then we don't have any more that rectangular shape. There are three main reasons why we have incomplete pump fillage. And that's one of the most common ones is gas interference. And it's very common because rod pump wells is usually an artificial lift system that is used in lower pressure reservoirs. So it's very common to see reservoirs that are way below the bubble point. So we have free gas coming from the formation into the well, and that free gas enters the pump. So depending on the pump sitting depth versus the perforation depth, but it's very common to see a gas interference condition in rod pump wells. Also very common to see a fluid pound condition, both really bad for the system. We'll be looking at why that happened, when that happened, and a third less common option for having an incomplete pump failure could be having a partially plugged pump intake. So there is something blocking or choking the pump intake, where we may have high pump submergency, but there is a physical restriction at the pump intake that avoids the fluid to enter fast enough to fill the barrel. And when the downstroke begins, the barrel is not full of fluid. So we'll be looking at different conditions and problems in the well that may cause an incomplete pump failure. So let's start with gas interference. Gas interference is usually characteristic when you have high fluid level. So you do have some pump submergency, especially if the gassier the well, the higher or the taller the column is, because you have very gassy liquid column. But at the pump intake, you have free gas. And you have free gas, and when the standing valve opens, there is liquid and gas entering the pump, and during the downstroke, what's in the chamber is a more compressible fluid. You have a portion of gas and a portion of liquid inside the pump chamber, and the plunger has to move down to compress those fluids until it exceeds the discharge pressure. So at that point, the traveling valve will open, and finally, we'll be displacing some fluids across the traveling valve into the tubing. So let's talk about first how gas works, how compressible is the gas. And basically, you can look at if you have any cylinder, and you can say this is 100 cubic inches, or you may see this is 100 inches stroke length, if that helps to visualize the example. So if you're the plunger squeezing those gas and liquid inside the barrel, you may have a 15 psi gas content in this cylinder. If you move this plunger down to compress that halfway, so you move 50 inches, you'll be doubling the pressure. So pressure doubles as the volume is cut in half. So we go from 15 to 30 psi by moving 50 inches. Then if you move halfway again from 50 inches to 25 inches, so you squeeze that halfway, the pressure doubles one more time. And you can keep doing that. You have now 60 psi, and now you have to move less inches. You have to move only 12 inches to go from 60 to 120 psi. What am I saying here? Well, the lower you go with that plunger, the less and less compressible those gases are, because now you have to move only 12.5 inches to compress 60 psi, to increase 60 psi. But before, you moved 50 inches and you only increased 15 psi. If we plot that, that plot will result in this one here. So you have an initial volume of 100, and you squeeze that to 50, and the pressure went from 15 to 30. And then from 50 to 25, and the pressure doubled. And then the pressure doubled again by cutting that in half. And that's how a compression curve works in a normal gas. If you look at that information, that's actually what you see in a typical gas interference pump car shape. So that curvature you see in a dyno car shape is actually compressing gas. That's a result of that curvature. So the shape of that curve will depend on how much initial pressure and volume you had in the chamber. The lower the pressure, the more inches you will have to move to compress gas to a higher pressure to be able to reach the discharge pressure, to be able to open the traveling valve. So compression curves are typical for gas interference wells. How did that happen? Well, we have a decompression zone at the beginning of the upstroke. Then the plunger moves all the way up after the standing valve opens, because the pressure in the chamber goes below the intake, moves all the way up. At the end of the upstroke, what we have in the chamber? Well, a portion of liquid and a portion of gas. Now the plunger will have to move to compress the gas and up to a pressure that exceeds the 2500 psi. So it will be moving down, compressing until 2500 psi are reached, traveling valve opens. Once that opens, it should move all the way down. Of course, there will be some gas still in the chamber. So the gas, but just passes first, and then some liquid will be pushed through the traveling valve into the tubing. Now, another thing to consider is the traveling valve opening point in the dyno car doesn't necessarily means that you have liquid from that point on, because actually, when you go from a lower pressure condition to a high gas pressure condition exceeding the discharge pressure, you still have high pressure gas. Once the valve opens, the gas will pass through the valve. You won't see that liquid in the tank. That's actually still in the gas phase. It doesn't have enough time to go into liquid. It doesn't change the phase. So you have some inches there that will be actually gas, and then you start having liquid being produced. So the software actually has a gas-free liquid line inside the dynamometer car analysis that I will show later. So the gas-free equivalent is a blue vertical line. So we'll talk about that. If you're calculating the pump displacement, barrels per day or cubic meters per day, by just using the traveling valve opening point, you may be overestimating the pump capacity. That you should be producing less than that if you're picking a representative dynamometer car. This car here, we can see how the upstroke loads in the pump. This is a clear gas interference car shape. We see the FO from the well, so this is a high submergency, and it makes sense with the fluid level information. So the FO line from the fluid level, which is calculated based on the fluid level information, matches with the upstroke load. So that's what you're expecting to see. You want to measure a dynamometer car. When you plot that, you want to see the FO from fluid level that matches that. That's very close to it. That's what we call those fluid level measurements, and dynacar measurements should complement each other. Now, when gas interference is severe, you may hear a common term that's gas lock. My well is gas locked, my pump is gas locked. Well, let's discuss about that at least briefly. But this could be a very long topic, and I'm going to just talk about that briefly. So I could just go and open a gas interference example, and I will go there in a second. So let's start switching to the software, and I have some examples here. Let me open gas interference before we jump into the gas lock. So this is a typical gas interference car shape, and you see how the upstroke loads are very close to the FO from fluid level line. We can see we have high liquid column, but this well is very gassy. So we have a pump intake pressure calculated, which is actually matching to the upstroke loads in this dynamometer measurement. So this makes sense. We have a high curvature. This is obviously not a pumped off well. We have enough fluid at the pump intake. But when we look at the gas, the liquid level, sorry, we see high gas, gaseous liquid column in the annulus. So typical dynamometer car shape for gas interference. But let's quickly talk about the pump displacement. So the software will calculate a theoretical pump displacement at 356 barrels per day. That's if the pump would be completely full, which is using the maximum plunger travel, and assuming the pump is 100% efficient, which is impossible. All sucker rod pumps have slippage. You have a clearance, a fit for that pump of so many thousandths of an inch. Is a very small clearance, maybe 3,000, maybe 5. Heavier crude oil, you may have -8, -10, and I have seen even -15 in really heavy oil conditions. But so the pump is not possible to produce as much. We can use the effective plunger travel, and if we consider this many inches of pump displacement, which is in this case 47.57 inches, the pump should be producing 111 barrels per day. But that is assuming the pump is 100% efficient mechanical efficiency, because we already have an incomplete pump fillage that we lose 70% of the pump fillage, which means we lose 70% of efficiency right there because of the incomplete pump fillage. But on top of that, we have some mechanical slippage, but also we have some gas in the pump. So when the pump was compressing and compressing the gas, we reached the pressure to open the traveling valve, but there is some gas in here. So you can go to the details and we see a equivalent gas-free fillage, which actually all this portion of the plunger was actually full of gas, high pressure gas to exceed the discharge pressure. And we only have a small amount of liquid, the actual liquid inside the barrel. So this pump is actually having this much liquid, but there are other things affecting the pump displacement. And as you see here, we are having a calculation of an adjusted pump displacement at only 42 barrels. So we're not trying to estimate or calculate 111 barrels per day. Very likely, if you gauge this tank, if you have a gas multi-flow meter, and you measure production in this well, you will be very close to 42 barrels per day, because we are considering multiple factors that affect that displacement. And those factors are the tubing stretch, and this pump is anchored, so we're not having much of that. The gas in the pump, and that's where the blue line goes in play. So we have many inches of stroke lost in the gas. The traveling valve close delay, we don't see much here. We see, because of the gas expansion, the standing valve opens at some point later. And we always will calculate some slippage. Now, slippage is another long topic to calculate, but you can have a better idea pump slippage if you go to the pump card analysis down here on the bottom right. And there is a multiple features in the software that you can understand. And there is a complete Ask Echometer session available in the website that talks about that. And I think it's called How Much My Pump Pumps. And that is related to understanding how is the pump displacement calculated, and that includes pump slippage. So one of the things that affect the pump slippage is the clearance. And the pump clearance is one of the pump details that you can input. So you will have a pump card as a physical card information about the pump that you get when you buy the pump. They will have the plunger diameter, the plunger length, but also the clearance. So the software will consider these factors when it's calculating the slippage. So when you go to the lift system, there is a rod string and pump information tab that you can include that information in here. You have very likely selected the plunger size, but you can go with more details. The bigger the clearance, the bigger the fit in the pump, you have more slippage, resulting in less production. So if we change and say, hey, this pump is actually 0.004 of an inch, if we save that information, the software will recalculate the slippage, having now more slippage and less pump displacement. You can have a pump that is actually has a 5-foot long plunger, and that being the longer plunger is harder for the liquid to slip. So you have less slippage, and the software recalculates that and have more production because you're losing less in slippage. And that's kind of a quick way to introduce that to you. I'm going to revert these values back to what it was. But there are many things that are accounted for calculating a more adjusted pump displacement. Hope that helps. Let's keep going here. So let's talk about a severe gas interference problem that may result in a car shape like this. Well, you can have maybe one stroke or so where the traveling or standing valve don't open along the stroke. And that's technically, for a few strokes, maybe a couple strokes, a gas-locked pump, what we consider a gas lock. Basically, traveling and standing valve do not open along the stroke. Traveling valve is going up, there is gas entering the pump, traveling valve goes down, compressing, but never reaches enough pressure in the chamber to open the traveling valve. That's technically a gas lock, like this car here. But if you want to look at one dyno car, you would say, well, my well is blocked. Well, the car may be deceiving when you are just looking at one, because if you look at multiple strokes, if you just stay recording, and that's one of the beauties of Echometer equipment, it allows you to do a more thorough analysis in a well when you keep collecting dyno cars. It's not like you have a controller in the well and you pull one dyno car or maybe two dyno cars a day. Where you have more dyno cars, you can see that actually there is a small, but still some pump displacement here. This, you see when the traveling valve opens right there. And if you look at it, this is one session. So we have multiple strokes overlaid. And the more you wait, yes, some strokes may look like gas locked, but the pump doesn't stay locked. It's impossible to remain locked. You still have a bunch of gas in the tubing. You may have a tubing blown dry, but the pump doesn't stay locked. The gas lock breaks itself. So you see, and then you can plot multiple dyno cars. You see most of the dyno cars will actually have some pump displacement. There will be some fluid production. Most of the cars still full of gas, but you have some gas. So the gas lock doesn't stay there. It can remain locked. Why is that? Well, because you have slippage inside the chamber. Even if the standing valve is not opening to bring fluid from the well, there is fluid falling around the plunger, and that's what we call slippage. Even a new pump will have that. So you have fluid falling through the pump clearance between plunger and barrel, and that's filling the chamber. As the fluid level inside the chamber is increasing, there will be more and more compression there, which will eventually reach the traveling valve opening pressure and will open that, and then the gas will flow through and some liquid will go out. Standing valve will open in that stroke. You may have a lot of gas coming in the pump again and will be locked for a few more strokes. But a gas lock is not a permanent condition. What you see on surface, when you open the valve on surface, the sample point, you may see only gas, but that actually doesn't necessarily reflect what's happening at the pump. You have to install a dynamometer sensor to look at what's going on at the pump and then understand what's the well doing. There is another concept that I will not spend much time in it, which is called a gas tagging. And this is a condition that appears in a well, in some wells, when you have a gas interference problem. And you can see this is one data set. This is 25 minutes of dynamometer data. And we can see first, in the first stroke, this is stroke number 17 in this data set. This is actually both this well also. These are in the examples that we sent you in that invitation. So if you open your email, there will be a TAM file attached. You can download those wells into your computer and practice with those and follow with these examples. So a gas tagging is another condition that may appear when you have gas interference. You see the full pump is everything looks good. Continue the reading at stroke 31. We have 79% gas pump fillage, so we have 21% gas interference. Here we have less pump fillage, but still a regular dyno car shape. We know this is not a pumped off condition because we have help from the well. So we have pump submergence based on the distance of these upstroke loads to the FO max. But when we look at the pump fillage, it goes below 70%, which is about the threshold point on this well. We can see a tagging appearance. So the pump is now tagging. And that tagging is making the car look like this, rattling, and you can see the reflections. Just like yesterday, we were discussing fluid level echoes of that sound wave traveling up and down. Well, this is exactly the same thing. This is a tagging happening on bottom, and that sound wave, that speed of sound, the energy is traveling through the rod string up and down and making these reflections along the rod taper, the rod string. Now, the car shape, this is, you see how loads are fluctuating as everything is shaking and vibrating. And that's a stroke 58. You see stroke 71 still doing the same. You still have the pump tagging. You still have the ugly dyno car shape. And then when the fillage goes up again, stroke 104, beautiful dyno car one more time. We have some gas interference, but nothing bad with it. So you will be having a lot of rod compression, a lot of shock energy traveling through the rod string, which will decrease the run life of this well. You will have a more premature rod failure based on this tagging condition. You may damage the pump. You will be, everything in the system will be suffering. So this is a very undesired condition. Solution to that, well, we have to deal with the gas interference. So why the pump was not tagging, and then at some point the pump started tagging down. Well, really, if you look at that dyno card shape, you have first you have a tagging that causes a lot of damage to the system. You see a surface card, you have a load that goes to above 26,000 pounds and goes down to close to. So we have about more than 5,000 or 6,000 pounds of load loss in an instant in the system. We see that reflection in multiple places. Another thing you have to consider is when you have a full pump, the surface stroke is the same, but the plunger stroke is different. So if you look overlay, and you can do that in the software, you can overlay dyno cards. If you overlay a full pump with a pump tagging and a more severe gas interference, you will see the plunger travel is different. And one of the reasons of that is when the plunger is going down, it's falling through the gas, not through the liquid, and it goes faster. It has a much higher velocity. So the instantaneous or plunger velocity is higher when it's falling and results in a longer plunger travel. Now, the industry has agreed in plotting the dyno card from the 0 inches line. Both surface and pump card will be forced to be plotted from the 0 inches line. So we have a reference. But what's actually happening is comparing those two scenarios, the pump is traveling 17 inches more when it's tagging. And actually that pump tagging is happening because all 17 inches is not because the plunger is traveling 17 inches higher. Those 17 inches are actually distributed, some going lower, some going higher, and that's why the pump tagging happens. We're getting very close to the break time. So let me close this idea, and we'll see a pump tag, how harmful that's for the system. So imagine you're the gearbox pushing that gear, and all of a sudden you lose, in this case, close to 7,000 pounds of loads. That put a lot of stress on all the components in the system. So even if you have a rod pump controller, when you pull the car, what are you seeing? Are you seeing the full pump? Are you seeing this beauty dyno car with just some gas interference? Are you seeing the real well problem when you're pulling a dyno card? So that's why having a more thorough analysis with Echometer is so beneficial. Obvious damages that you can find when the pump's tagging down. You can see this is a very common condition. Some people say you have a slide tagging. Well, light tagging, because you see a small spike in here, that's actually thousands of pounds of load being applied to the bottom of the pump. So you're actually have a couple of 1,000 pounds hammer on the pump on every stroke, thousands of times per day, which will lead to problems like this, or even this is a pump hearted on the bottom of the barrel, where you can see the seating nipple mechanism there. Let's go with the next topic, that would be pump off condition. So we have been exploring options or reasons why we don't have a full pump, and one of the things is we had free gas at the pump intake and at the upstroke when the standing valve opened, and the gas and liquid was able to enter the pump, and then we had to compress it. But now let's explore cause number 2 of having an incomplete pump village, and that will be having a pump off condition. The well, it's a normal phrase that we have, a pumped off well, meaning we don't have enough liquid at the pump intake to fill the pump. So we're basically over pumping the well. If you shoot a fluid level in this condition, what you should observe is you have the fluid level very close to the pump intake, so the pump intake pressure is low. And what's happening is you're going either too fast or too long, or you have too big of a plunger. Basically, you're pumping too fast, and you don't have enough fluid inflow from the reservoir to fill the pump. In these scenarios is when you have to opt for different options, either slowing down by installing a different pulley size, or if you have a VSD grade, you can just go down and decrease the hertz, or decreasing the stroke length, or next intervention, you may need to install a smaller pump. If you have already tried all that, you're running at the minimum speed, so you ensure good lubrication for the gearbox if that's a problem or a concern. You have the lowest stroke length, so you're in the minimum hole in the crank, but also you have a small pump in the well already. maybe you just don't have enough inflow to be able to match that inflow with your pumping capacity. Then you have to opt for options like stopping the well for some time, turning on, which a pump off controller will play in, or a timer, or something that allows you to decrease the pumping rhythm. So what happened in the pumped off condition? Well, the car shape is different. First, we will have this shape where the upstroke logo goes up and then goes down, and then the car shape, yes, will change based on, again, if the tubing is anchored or not. So we have that reference of a rectangular or slant to the right dyno car, and we see that slant to the right dyno car shape. And again, maximum plunger travel, effective plunger travel is different because we have some incomplete pump fillage and plus the tubing movement playing there that decreases the effective plunger travel. When we see a dyno car shape, that's a common thing. Upstroke loads go up, then downstroke loads remain high, and we have a sudden load decrease. And we could say, well, this is kind of a curvature here. Isn't that gas interference? Well, remember, gas interference, you normally have some pump submergency, which means the upstroke loads are normally far from the FO max line. But in this case, there is no help from the well because there is almost no pump submergency. If you see the pumping tape pressure is very low because we have very low pump submergency. So the FO max and the height of the dyno car are almost the same. That's a common condition for a pump off well. So when you have a well that once you start it is full pump and a few strokes after it just becomes a severe fluid pound, that's normally a candidate for a rod pump controller. Again, if you're already pumping slow, you may try to, depending on the well production, how much you're making from the well, you may install a VSD or a timer at least, but having a way to not pump the well in a fluid pound condition, which is very harmful. You have to find a way to match the inflow capacity from the well. Another example here from TWM, very low pump submergency, car shape, has typical going upstroke, downstroke, flat lines, and all of a sudden, boom, it goes down. So we see a well that has a fillage that is very low, that's less than 50%. And this well is not running too fast, so 6 strokes a minute. We see different conditions where pumping speed like this one is going above 11 strokes a minute, despite that the pump fillage is less than 50%, so that, or around 50%, in this case, 52%. So this obviously going too fast and you have room for optimize the well. And someone has to take the action and say, hey, we're going too fast. We're over pumping this well. To explain what happened is the plunger is moving up and you can plot this. There is an analysis plot section in the software that you can use to plot the plunger position, and that will be represented by the blue line. And this is how fast the barrel is filling up based on the available fluid at the pumping tank. So the plunger is filling, the plunger is moving up faster than the liquid rate entering in the chamber. So at the end of the upstroke, the plunger is all the way up, but the barrel is still not full of liquid. So the downstroke begins while the barrel is still filling up, and at some point, bang, that happened. The plunger finds the liquid. Kind of, you have a very high pressure there right before, but let's say that's when the fluid pound condition happens. And the difference that I like this slide because if we have a car shape like this, that loads drop fast, or the loads drop gradually, more like a gas compression, is the only difference between a gas interference and a fluid pound is how much gas pressure you have. Because at the end of the upstroke, you have the same components in the chamber. You have some liquid and some gas. When you have gas interference, you have some liquid and some gas, and the same when you have fluid pound. So what is the difference between those two? Well, it's the gas pressure. When you have a fluid pound condition, the gas entering the pump is a low gas pressure because there is almost no pump submergency. So low gas pressure will require more inches to increase the pressure, and all of a sudden it drops. That's what we see in a fluid pound condition. While in a gas interference condition, you have high pressure gas entering the pump because the gas bubbles at the pumping tank are at high pressure due to the high pump submergency. So it's basically the same components. The only difference, again, between gas interference and fluid pound is the gas pressure in the chamber. There is always problems when you have an incomplete pump village. You have rod compression, the rod buckles creating all sort of problems. And if you can see here in the picture, you see how many, probably thousands of times this rod coupling at the same point has been banging the tubing multiple times to make the print. You can see actually part of the rod head, and you see the coupling here. So it's very obvious that this well has been having an incomplete pump village, a fluid pound condition for a long time. This will lead eventually to either a parted rod or a hole in tubing. So that's why we don't want to pump the well in these conditions. Now, if you have this dyno car shape, upstroke loads matching the FO max line, incomplete pump village, boom, going down, we would say this is a pump off condition that has the same characteristic of the rod pump, the fluid pound condition. But there's a third reason why the pump could not be full of liquid. So another reason for incomplete pump village is having a choked pump, an inflow restriction. Something is blocking the flow of the fluids into the pump, and that could be caused some paraffin or scale or sand tops or asphaltines or anything that's building up in the well, some solids that enter the pump, like sometimes some rubbers, some plastics, so gets into in the way of the flow, like in the chamber or the cage, and it blocks mechanically the path of the liquid. So in this condition, you see that you have pump submergency. You see liquid level is above the pump, but you still see a choke, a fluid pound shape. Another thing that we see is that we see negative load. So that's a good indication of having a choke pump intake. In this well, for example, we have a high pump submergency. Pump intake pressure is really high, 1400 psi, but still we don't see the pump is full of liquid. So how is that possible? Well, we have a choked pump intake. There is something restricting the flow into the pump. This is another example now from TWM, high pump submergency, 857 psi of pump intake, but still fluid pound condition or car shape. And now we see a difference. So we see not only the upstroke matches with the FO max line, but also the fluid level line is below the car shape. So if we don't have that restriction, the height of the dyno car could be down here in the blue line, but it's not there. Examples of pump restrictions. If you see some buildup and there's a lot of scale in these wells, sulfur iron, anything that's blocking the signal, you see how severely choked is this pump. So this were good pictures from Justin. Now another thing you can see, you have a strainer nipple, and you see how much buildup. You see these little holes that are supposed to be the flow area is almost all clogged. You have some flow area, but most of it has been restricted. So that's a problem that just broke during the pull out, but this is how that strainer nipple is down the well. So we don't recommend to use strainer nipple. That adds blockage to the system. You have things like this, debris in the well. All these are normally bad decisions for your pumping system, especially if you have trash going on, because that will block the intake. Okay, another topic we need to discuss is traveling and standing valve analysis. So one of the measurements you can do with Echometer equipment is, regardless if you use a PRT or a Horseshoe load cell, you can always do a valve analysis. That's basically stopping the pumping unit in the upstroke and the downstroke. And we will analyze some car shapes. So there is a by the book car shapes. Upstroke loads will look rounded in a traveling valve condition. But let's see how that looks if the pump is okay. So if you have a pump that's working okay, you have to stop the pumping unit on the upstroke, let's say 3/4 of the upstroke, and look at how the loads behave. Remember, you're holding the polish rod that's holding all the rod string, and during the upstroke, the traveling valve is closed. So we're also lifting the fluid loads. Stopping during the upstroke on surface, we're holding the rod string weight plus the fluid weight. So we have more pressure above the traveling valve than below the traveling valve because the standing valve was open, and it's almost equal to the intake pressure. So we have differential pressure across the traveling valve. If we stop the pumping unit, this is real data from Echometer. You can, after you record the dynamometer data, you go to raw data, and there will be a valve analysis if you stop the pumping unit. When you find that, double click here in the valve analysis, and that will take you to the valve analysis window. Now you can enable the traveling and standing valve test, and this is what you see. Every time you see a gray line is the pumping has been stopped, so acceleration is measured like close to 0, and the software see the loads. So this is loads versus time plot. If when you stop the pumping unit, the loads don't change, that means the traveling valve is working good. Going to the downstroke, we don't have fluid loads, just the rod string weight. So the rod string weight in static conditions is about 8,000 pounds. And the loads remain there. Another standing valve test, loads remain there, and that's good. Traveling valve is good. And eventually, because we have pump slippage, that load will gradually go down. And this is a couple of minutes of time. That's just because of the pump slippage. This is not really pump leakage, as the pump always have some slippage. If you can put a band to calculate that, and the software will actually calculate that for you. The software will calculate this slope, because if you learn about valve analysis, say if the loads are going down, the pump is leaking. Well, not necessarily. This load's going down, but in a long time, it's just a natural pump slip. It's only 1 barrel per day leakage. So the pump car shape looks okay. Traveling valve stops okay. Standing valve stops. So this test is a representation of a good, healthy pump car or pump condition. Now, if the traveling valve is leaking, then the car shape will change. It will be round on the corners. And when you stop the pumping unit, the loads don't remain up there. The loads go down. And you can observe how the load drops because there is differential pressure across the traveling valve is lost. So we see some examples of that. I'll show some examples of traveling valve leakage. So standing valve loads. If we have a traveling valve leakage, the dyno car shape will look like this. So it will be kind of round in the corners. We don't have that square shape in the up portion of the dyno car. This is a representation of a leaky pump. You have from this point, when it's flat, actually, this will be the effective plunger travel from the standing valve opening to the standing valve close. That's the fluid that entered the pump. So if you want to quantify, you will have a hard time to estimate a good adjustment unless you tell the software this is the adjusted plunger travel you want to use. This is a more severe one. You can see it's round all the way. It's not even getting up to there. So this pump is very likely not producing. And we will have examples of that in a minute as well. So completely round, this is what we call not a leakage, but it's a worn pump. It's a worn out pump. We don't really know if it's through the traveling valve, but most likely it's between plunger and barrel assembly. So let's look at some examples of that. So let me jump to the software and let's go with a traveling valve leakage. So this car shape here. If you look at the dyno car shape, you see there is some rounding on the upper corner. There's some more rounding here, maybe even some of the delayed traveling valve closure, but that's another topic. We for sure have rounding shapes on the upper corner. So based on the car shape, we're expecting to see some traveling valve leakage. So what we do, we can go to raw data and click on that. So we have a valve analysis, valve test. We can double click on the valve test and get here. So we see the loads are dropping. The traveling valve, you can see here that the gray zone stopped, that you have to get some slope. And we'll see this pump is leaking over 21 barrels per day. And we stop again and we see the loads going down one more time. So we have evidence, not only from the car shape, but also from the valve test that we actually have a pump leakage. Now, the standing valve. The standing valve is the opposite shape. So we have a lower corners of the pump car being rounded. And yes, the car shape changes between anchor or an anchor tubing, but basically you will see the rounding on the lower portion of the pump car. Now, when the standing valve leaks, what happened is during the downstroke, you stop the pumping unit. The pressure, initially the pressure inside the chamber was high as the discharge pressure, but when you stop, the pressure starts leaking through the standing valve, meaning the chamber pressure goes down, and there is now a differential pressure across the traveling valve. As we have been always holding the polish rod connected to the rod string connected to the traveling valve, we are always measuring traveling valve loads, but we can use that information to measure standing valve leakage. So this is a typical car shape. It's rounded on the corner, so we know this is a standing valve leakage. And if we calculate the effective plunger travel, we'll have to account for the traveling valve opening point to the traveling valve closing point. That's when the plunger was transferred from the chamber to the tubing. This is a valve test. Traveling valve loads are okay because the traveling valve is holding good, but the standing valve, every time you stop the pumping unit, loads go up. Again, standing valve stopping, pumping unit, stopping the pumping unit, loads go up. So that's a representation of a standing valve leakage, and you can confirm that information by performing a valve test. This is a severe standing valve leakage. So that's a worn out pump. It's a worn out valve. So we see very little pump effective plunger travel, and this well may not even be producing anything. You see how far it is from the FO, so maybe an indication a pump that is not producing. Actually, this well was not producing anything. Let's look at an example of a standing valve leakage. Let's go back to the software. Peak well, standing valve leakage. Let's look at the dyno car. Again, round shape. If you look at the events, you see most of the car will have the round lower corners, and that's again an indication of a leakage. Go and check this the valve test. You see traveling valve holding, stopping, going up, stopping, go up again. And you see how the loads equalize to the traveling valve because the standing valve can't hold any loads. It equalizes, so the traveling valve actually start holding the fluid load so the fluid doesn't go down to the valve. When you're acquiring dynamometer data, many of the questions we have is actually due to weird car shapes. People call and say, hey, what is going on with my pump? This is a weird car shape. Most of the time it's related to data input. So things that you have to account for, remember the rod description is important, pump information, fluid properties, surface pressure, you have to measure tubing intake, tubing pressure, sorry, and the pumping information are critical to have an accurate result. So if you see something weird, check the data, check the inputs, and see if that makes any changes. So by having run input, you go from a dyno card shape and bottom, like from this to this. So surface card is the same, but how we process the data based on your input is what makes the difference here. So we see a full pump, so rectangular. We have high pump submergency. We see the difference between the FO max and the absorbed load, and we have a hard tagging down. We have probably more than 1,000, 1,500 pounds of pump tagging. So we can tell now that we couldn't see anything before. Now we can tell what's going on in the well. Full pump, high pump submergency, pump tagging down. This pump needs to be respaced. We go from this dyno card shape. So what's going on here? It's hard to tell. Maybe you have a severe barrel problem, but no, it was just the data input. Go 7 inches to, 3/4 to 7/8 to 1 inch. Actually, it was upside down. When you enter the information in the software, you have to go from surface to bottom. What's the upper taper, close to surface to bottom to the pump. So 1 inch to 7/8 to 3/4 is actually the configuration in the well. And that fixes the card shape calculation to a full, beautiful pump. Another data input problem, 1/2 inch from 1 inch to 1/2 inch, actually was 1 inch to 7/8, which is normal. And it goes from slant to the left, normally a bad indication, data. But when we fix that, we see some slant to the right, maybe it's a little bit of pump, traveling valve leakage, and an anchored tubing in this well. Another thing we can determine if you're using a polish rod transducer is a great tool because it allows you to see things in the field that you may not be aware of. And that one of those things are very harmful to the system. That is a misalignment. So if you have a bent polish rod due to a pumping unit misalignment, you can catch that normally with a PRT. As the PRT is so sensitive, we in a normal straight polished rod, you could have a circular shape if you have a cross-sectional area of the polished rod, but if you bend the polished rod, that is not a circle anymore. It becomes more like an oval. So that results in just unreal loads being read by the PRT, and that will result in normally slant, either pointing up or pointing down dyno card shapes. And that's usually an indication of a bent polished rod if you measure that with a PRT. So you can now measure setback side to side, just check the horse head, the carrier bar, and make the alignment necessary for that pumping unit. But this is misleading because now you have a problem calculating the pump stroke. There is a maximum plunger travel 75 or 109, and this is the same well. This well had a rod rotator, and it was rotating, and after you have some other degrees or orientation at the polished rod, now it's pointing down. But actually it's the same well, and we should have a more flat dyno card. Let's see if we have time to show an example of that. This example here, a severe traveling valve leakage. This is a worn out pump. Basically, this is worn out. You see one dyno card, you say, well, I have to replace this pump because the card shape tells me the pump is worn out. Well, hold on a second. If you look at all the data, and that's the beauty of having a dynamometer from Echometer, is you can overlay multiple dyno cards, and you can see some of the cards, actually the previous cards, had some pump displacement. You have a delayed traveling valve closure, but actually the traveling valve closed, and you were able to leave fluids, and you're pumping in this well. So this is normally an indication of a damage on the traveling valve or the seat, or some dirt in the pump. Another problem you can face is a hole in barrel. It's a split barrel. And that is meaning when you're going up, that must be a insert pump, a bottom hole down, where the pressure is distributed around the pump. And if you have a split barrel, you have a hole in the barrel, the plunger goes up, and you see a good load pickup, goes up, and then the pressure drops. Pressure drops, and from that point on, you have no production. So the effective plunger travel is very small in this well. Basically, what happens is this: when the plunger passes the hole, the pressure above the traveling valve, which is also around the pump, because this is a bottom hole down, it enters the barrel. So now the pressure above and below is the same. So we lose the fluid load. The fluid loads are lost, and now the fluid weight rests on the standing valve and the tubing. So we lost the loads. That's another example of that. And this is a picture of the hole in barrel that was causing this dyno card shape. You see normally a over travel in this type of well condition. You can monitor the plunger velocity and the polish rod velocity. So the plunger, as the polish rod is moving around 30 inches per second here, the plunger takes off and moves more than twice the speed, resulting in an over travel in the pump. So now in this case, the pump is moving more than the polish rod. Pumps tagging down or up is a bad condition as well. And you can tell by looking at the lower left corner or the upper right. In this well here, yes, we have multiple things. We have a thick nose, usually an indication of some friction in the system. We have incomplete pump fillage and maybe a curvature, but I think it's more a fluid pound because I can see the loads are actually above the FO max. And we have a pump tagging down. This is the point of this slide. It's showing a hard pump tagging down, and that pump needs to be respaced. Another pump tagging close to 2,700 pounds. Here we can see that peak or spike at the surface, but you see the pump tagging down real hard, maybe due to that incomplete pump fillage. Another problems. You send me the data and ask, hey, what's wrong with my well? Well, somebody is not inputting the data right one more time. We have a 4.1 surface stroke. Well, that may be a pumping unit on my desk. But this actually, the surface stroke was actually 144 inches. And now the software is able to properly calculate the pump card. It's a full pump, lots of rod stretch. You see the pump is not moving as much as the surface, but you have a hard pump tagging down. So one more time, run data input leads to run analysis. And that takes me to one of the last topics, is flat dyno cards. The flat dyno cards, when you get a flat dyno card, you may think in multiple reasons. If you make a measurement and you see a flat dyno card, that could be a parted rod, either shallow or deep. But if you have a problem in the pump, having the traveling or the standing valve that is stuck open, you're not pumping. If you're not pumping, you can see the plunger going up and down, but there is no fluid loads being picked or dropped. So there's no low fluctuation, so you have a result as a flat dyno car. If you have a well that has a tubing blown dry, if you have a well that is having a fluid level at surface, so the pump is not doing anything, we call that condition flumping. So fluid level in the annulus is being, actually you may have some production on the backside. So there is enough pumping type pressure to keep traveling and standing valve opens. And so you, as a result, you have minimum to no fluid loads and the flat dyno car appears one more time. So there are multiple reasons why you can have a flat dyno car. And these are some of the reasons. A traveling valve stuck open, a deep or shallow parted rod, a tubing blown dry, a standing valve stuck open, or a blood pumping tape. So how do we know which one of these dyno cars am I facing? Well, you will have to check all the conditions. Is the well producing? How does the pumping unit looks when you stop the pumping? Is there any fluid coming in the backside? Do you have normally severe gas interference? Were you having gas interference, or were you having a pump off condition where that may lead to a parted rod? Is a parted rod a common problem in your well? But if you measure this well with a PRT, you will always have a flat dyno car that will always be plotted on the zero load line, because that's what the software is designed to do. So every time you see a flat dyno car, you want to use a horseshoe load cell to measure direct loads, to quantify how much load you have on the polish rod. And the position now of that flat dyno car is what's going to tell you what of these options is what's going on in your well. If you have a shallow parted rod, that will be below the zero load line. If you have a traveling valve stuck open, then it goes up and down and never lifts loads. If you have a standing valve stuck open, the traveling valve carries the loads all the time, go up and down, and the flat dyno car will be up here. If you have a tubing blown dry, that will be above the zero load line, because there are some rods in the air, in this case in the gas, but there are some rods that are not submerged in liquid. So there is no buoyancy rod weight, but it's heavier rod string as calculated by the software, which puts the flat dyno car above the zero load line. So let's look at some of those examples to better understand what problems we're facing. This well here goes from stroke 11 to stroke 13. Well, full pump to zero. Well, do we catch the point where the rod's parted, or is more likely that we catch the point when the dirt enter the pump and we have a trashy traveling valve, which made the traveling valve to get stuck open? If you see that flat dyno car on the zero load line, one of the things is to have either a really deep parted rod, or you can catch the time due to this delayed traveling valve closure, there's some dirt in the pump. Another flat dyno car, now on the zero load line again, you pull the well and there's a pull rod unscrew. So there was a rod string complete. It was parted or disconnected right on the pump. So there will be again on a zero load line flat dyno car. Normally you see plunger and polish rod velocities being very similar in this way. Now, if you have a flat dyno car that's way below the zero load line, that's usually an indication of a shallow parted rod, because you have missing rods. The software is calculating the pump car, assuming that you have a rod string complete, but the rod string is actually parted. So when it, let's say, subtract the rod string weight from the surface car, the calculation on bottom goes below zero because you have some missing rod. Actually, you can have some calculations to see and have an idea how many rods you have missing. So all these are conditions, and I will have some examples of that in the next minutes. So this is a summary slide to talk about the location of the dyno car shape. Will give you an indication of what the problem is in the well. Now, if you have any question, I can do it now, or I'm going to jump to the examples instead. Back to the software, and let's look at some examples here. I have a good number of examples. So kind of going backwards, I'm going to show a fairly flat dyno car. And low fluid loads, one of the reasons was having a high fluid level. I'm going to look at these fluid level shots, and Actually, we don't see much of a fluid level. Kind of putting together the information yesterday with what we have today. We don't see a liquid level kick. Here, we don't see a liquid level kick. Actually, the software doesn't recognize to say auto liquid level detail detection failed, and you have to manually relocate that. But we don't know where the fluid level is at. Well, we don't know where the fluid level is at unless you close up. And one of the things we told you is inspect the first second. If you focus on the first second of data, actually now you can see a liquid level kick and a repeat and a repeat and a repeat. And actually you can see 1, 2, 3, maybe 4 colors. So you have a fluid level is very close to surface after the pressure build up some, which leads to a flumping well. It's a flowing well, and that's why the pump is not doing almost anything. And by the way, there is a bent polished rod. You see how this curvature that shouldn't be there. That polished rod or that pumping needs to be aligned. Another example here, we have a fluid pound condition. So we can see a fluid level shot one more time. We see an up kick from the perforation, and we can use that. Or the color count was good enough. We can use either or a perforation top, and let's just do that, and we see how the fluid level can be calculated very close to the pump intake. So we have a liquid level and a pump intake that's actually only like 7 feet, which matches the car shape. So when we shoot that, we're expecting to see a fluid pound, and actually we see that. We have the events, all the cards will be pumped off. You can see by clicking on event, an overlay of that. So it's pumped off, and all of a sudden loads go down. Okay, that's a typical car shape for fluid pound condition, putting that together with the fluid level information. We have a normal full pump. We have some pump submergency. We see on the dyno car shape, in this day, the pump was full, rectangular car shape. We don't have a lot of pump submergency where we have some. You see the difference between the FO from fluid level and the FO max line. And the FO from fluid level line matches the upstroke load. So we have a little bit of pump submergency, and we can see that here. But this is a full pump, so I think they're doing a pretty good job on this well. You can always obviously print the report, and if you've been doing inputting the information in the software, you don't only have the fluid level information, but the car shape will give you pump displacement. You have the rod string loading as well. That's why we use surface cards for peak load and minimal load to calculate the rod string loading. There is a gearbox existing, so this is just a little bit heavy weight. So that's way heavy here, but still not overloading the gearbox torque. So that's part of the interpretation of the gearbox. If you want to balance this pumping unit, really it's only having to move 3 inches. It's not gonna gain a lot on that. So maybe for 3 inches, you don't want to spend the time and the money on the crew to go and balance that pumping unit yet until the condition changes. Another well was the gas log and tagging. You saw that. And we have several examples of holes in barrels. So holes in barrel will be basically an upstroke load, and all of a sudden the load drop. So we have a hole around this portion, and the loads will drop after the point. So this pump is producing, but has low efficiency because the stroke, actually, if we want to account for displacement, would be from this point on, or we could say from this point on. So the pump, the software, we should be able to calculate just using this stroke length, this effective plunger travel. This is a good example. Let me use some tools here. So when you look at one dyno car, you see, wow, it's really round, and this must be a severe traveling valve leakage. Well, one of the things you have always to do is compare the dyno cards, compare the car shapes, and see how are they behaving. We see that dyno car, but we can overlay a few strokes before with this dyno car. And let me go to field view so we can see the overlay. By clicking on your keyboard, the control key, you can overlay some dyno cars, and you see how this car is more rectangular, looking good, the car shape. This one is not that bad. So we have a changing leakage. Like this is really bad, this is better, this is much better. some leakage, some leakage. Some of those are like this one's really bad. So on this stroke, the pump didn't produce anything. So what could cause that change in the pump behavior? Well, a pitted ball would cause that. So we have a traveling valve that is severely pitted. That could cause that sometimes it sits on the seat in a good way, providing better seal, and some other strokes like this one would be terrible. So that's another way to see how this changed that much. So you have some strokes like this one, dyno car is very good. Some strokes are really bad. Let's look at a parter rod. Flat dyno car. Well, we don't know. We have multiple reasons for the flat dyno car, but when we see the flat dyno car measured with the horseshoe load cell, now we can trust on the location or where is this plotted in the vertical axis, and it's below the zero load line. If we look at the details, the pump car is below, it's a negative thousands of pounds. So yes, it's below the zero load line, and that is an indication of a shallow parter rod. So we have missing rods here, a couple of thousand pounds of missing rods in this well. It's a quick, simple way to diagnose the well. You lost production, you go to the well, you measure, and you see you still have some weight because you're lifting around 6,400 pounds of loads, but the rods, the pump car is way below zero. Another well here, severe pumped off condition. So well that's producing like this, well, it's not bad. You have what? This is a 50% pump fillage, maybe a little more. Change that, 52% pump fillage. But is that really a 52% pump fillage? Or remember, when you are going to install the sensor, you have to stop the pumping unit. If the well is pumped off, and you can check the fluid level information, you can see some perforations, and this well didn't have good details on the perforations, deep fluid level. Looking at the dyno car, you can tell, well, it's pumped off, but I should be producing 52%, so equivalent to 82 barrels per day. When you come to the detail view, adjusting by slippage and an anchor pump and so on, you should still having like 72 barrels per day according to this dyno car. But when you look at more strokes, and that's why it's important you to look at the events and allow the software to collect data for at least the time you had the well down. And at this point, this data was recorded for only 8 minutes. If you only record data for 1 minute, this well is pumping at 11.4 strokes per minute. So if you record for 1 minute, you'll be here in the 11 dyno car, still having 53% pump fillage. But if you allow the well to run some more, eventually you will see how that car fillage goes down to almost nothing. So you can overlay the car that you were trying to analyze, which is not correct, because when you stop the pumping unit, the fluid level went up, start the pumping unit, start to go down, to the actual condition of the well. If you look at the dyno cars after that, they're all completely pumped off. So basically, this well's not producing. We see a little bit of liquid here, but this is just pump slippage. There is no fluid coming from the well. It's very minimum to no liquid coming from the well. So there's almost no production. But they're still producing the well at 11 strokes a minute. That's crazy. So someone is not doing the job here. This well should be in a downtime longer than what it is. Okay, we have some pump cards that we want to look at before we finish the session, and look at this card shape. And this is more consistent. So if you overlay dyno cards, they remain the same. So this is the actual condition of the pump. You have a severe pump wear in this example here. So I don't think that's through the traveling valve only. That's normally plunger barrel assembly. So it's a severe pump wear. You don't see any flat portion of the dyno car, so very likely this well is not producing anything. But it has the potential to produce hundreds of barrels, but this pump is worn, and now it is time for you to go and fix that, because the well is already running at 9 strokes a minute. You can sometimes compensate traveling valve leakage with more speed, but in this case, I doubt that'll be an option. Good example here of an anchored tubing. So you see this dyno card shape, slant. The software have the capability of plotting things and annotations. We can plot that like the rods stretch on the pump card. That will be the dyno, this flat dyno card. The red KT line. And we can tell if the software, we have input the tubing anchor or not by looking at the drawing, or you can always go to edit and look at the mechanical wellbore information, and there is no tubing anchor in this well. So we're expecting to see some inclination because of the tubing movement. But the slope of this dyno card is even more than just the tubing and anchor line. So we have a little bit of slippage here, but this is definitely in an anchored tubing. Now, the previous example, that was a year ago, a year before that test, the well was pumped off. You can see a difference on the stroke length, but also you can see the pumped off dyno card shape in an anchored tubing. So you see an inclination, you see a flat card coming back and then going down. We don't have the fluid level information on that date, but we can see from a fluid pound condition and anchored tubing to a full pump and anchored tubing condition. Let me see what else we have here. Let me find a picture of that. Okay, Justin, do we have any question? Or I can pull another example that I would like to talk about.
Yeah, we actually do have some questions if we want to roll into our question and answer session. And so we've got some good questions here that we'll take these last few minutes to present, and then ultimately Gustavo or myself will answer. So the first question that we have, it looked like it was coming from Egypt. And the question was, can I input data from my controller into TAM for analysis?
Can I go with that, or you want me to?
Go ahead, Gustavo.
Well, common question. I have a rod pump controller in my field, maybe a SAM controller, a Lofton controller, or different type of controller. I can pull the data in my SCADA system, or I can download it somehow. Can I analyze the data using Echometer system? Well, there is no compatibility between the systems. First, the data that's being input from those controllers has a much lower resolution than what we handle. We, at least at the lowest rate in a wireless system, we are sampling at 60 hertz, which means every second we are collecting 60 points of data, 60 loads points and 60 position points. So in this, like this example, we have a pump unit that is running at 4 strokes a minute. So we have about 15 seconds of data. So we have about 900 points that makes this plot. That's way more than what a pump controller can do. And the way we process the data, it's not compatible with what you have from a rod pump controller. So this is not a diagnostic software that will accept data from an external source. This is a software that is compatible with Echometer sensors and will give you much more details and calculations based on a single sensor. Another reason why we're getting more quality data from this one here is because both load and position from a dynamometer sensor comes from the same sensor. When you have a controller, you have a load cell that's giving you load, and from a different sensor, a Hall effect switch or an inclinometer or potentiometer or some other source of information, you have the position. Then that position and load will have to be matched, and sometimes they are not in sync, which give you, like, for example, a top of stroke problem where the dynamometer car slants to the right or the left and start giving you weird shapes, unrealistic pump car shapes. It doesn't show good pump tagging down. So no loads or dynamometer cards from a controller are not compatible with Echometer technology.
Okay, good, very well explained. So the second question we have is, and we actually have an example of this. You may have to refer back to a presentation to get to it, Gustavo.
Sure.
But the second question is, do we have an example of a card showing a tubing leak?
Oh, yes. Let me go and pull. Well,
While Gustavo's looking for that example, just to maximize our time and give him an opportunity to pull it up so he can further explain it, one of the questions that I think that I can answer while he's looking for the information is, can I use a polish rod transducer to conduct valve test if the polish rod transducer doesn't measure real load? One of the things that we emphasized was the difference between how the measurements were made between the horseshoe load cell transducer and the polish rod transducer. You can utilize the polish rod transducer to conduct valve tests. Okay, there is not an issue with that whatsoever. Now, there is a test that we didn't cover today, which was called counterbalance effect or counterbalance moment, CBM test. And ultimately, with that, you have to use a real horseshoe load cell transducer to measure that because you're measuring real load. Okay. But the answer to that is that yes, you can utilize the polish rod transducer to conduct valve tests to measure the slippage of the traveling valve and or the slippage from the standing valve.
so I could have I don't have a handy example of the hole in tubing, but I have an example that talks about having a partially empty tubing, which is a well that was measured right after workover. And we can see how when we start recording, we have a flat dyno card. We have a flat dyno card that is not resting on the zero load line, which means it's not a deep parted rod. That flat line is not below the zero load line, so it's not a shallow parted rod. On the FO from fluid level, we don't have a dynamometer card that is up here that is showing a stock standing valve, but we have a dyno card that is flat, but it's some pounds above, which is normally an indication, if you remember that slide, that's a tubing blown dry. Well, this well actually has a portion of the tubing dry because the well is after a workover. So they fill the well and the tubing is empty up to the liquid level in the annulus. So we have some weight of the rods in the air. And I have just a couple of minutes to explain this one. But this data set is very interesting because we started recording having a flat dyno card because the discharge pressure due to the liquid level in the tubing, having the discharge pressure similar to the intake pressure due to the liquid level in the casing. So the differential pressure across the pump, intake versus discharge, was very similar. Now, if you look at this slide, I can overlay some of the strokes, and we have a gradual increase in the loads. And let me just do like 20 at a time. So as you can see, first stroke was, then you have some loads increasing, and the dyno card shape, you see how it's getting some height and more height and more height. And that's because the fluid level inside the tubing is going up as the pump is producing. So the fluid in the tubing, or the pump is filling the tubing with fluid. Now the discharge pressure is more, and we have more differential pressure in the pump. So after some point, we have a stable full pump that matches the fluid level in the annulus. That's exactly what you're expecting to see in a healthy producing well. So we had at stroke 300, I was making notes, and when stroke 300, the fluid then finally reached surface. And then after that, we have a more stable dyno card shape. So we go from a flat dyno card, low fluid loss because there again no differential pressure across the pump, to a full beautiful pump when the pump was able to fill the tube and start pumping continuously. So that's the importance of having a reference line like the FO from fluid level and FO max. And yes, the difference between those two would be the contribution of the well from the fluid load from the fluid level, and the rest is having a match from the upstroke loads to the FO from fluid level. So good example to explain how fluid loads work. We didn't have fluid loads or differential pressure across the pump at the beginning, and then at the end we were pumping normal. Another question, Justin. Can I use the, so one of the question is, can I use the PRT to conduct valve test if it doesn't measure real loads? Yes, and I can show multiple examples of that. So the PRT will be able to calculate the pump cards and will be able to calculate the load difference. And when you want to see how the load changes and when you stop the unit, when you stop upstroke to test the traveling valve or stop during the downstroke. Let me see what we have in this well, if we have any valve test. Most of this will be with the Horseshoe, but I can find some PRT load cell, a PRT valve test. Okay, this is a valve test performed with a PRT. I don't know if we have any other here. Well, we have one here that we can observe. Traveling valve, slide, slippage, standing valves staying flat, standing valve staying flat. So yes, we can perform a valve test, and this pump is healthy. We see just a slight load decrease equivalent to about 2 barrels per day. Standing valve is healthy, and we can look at the dyno car shape. And as we can see here, we have a little bit of slippage only, but it's a healthy, mainly a healthy pump. So we have a full pump, and that reflects also in the valve test. So yes, we can do it. As you can tell here, this is a WPRT, it's a wireless polished rod transducer. You can tell that in the test information, WPRT. Can valve test measure well friction? And I had an example let me find that residual friction. If you have a leaky pump and you have to let the well to go all the way down. Let me get here, this one. So something you can do is you can wait long enough to see where the traveling valve load will stabilize. And if you're going up, you may have you may be holding some friction, but also the pump slippage will be released. If you have any difference after many minutes between the standing valve load and the traveling valve after the residual load, you may see some friction difference. Another indication of friction will be the dyno car shape. If you have a thick nose in the dyno car shape, that's usually an indication of friction. Surface car will also indicate if you have friction in the system. Friction may be from different sources. Even an over-tightened stuffing box will give you some of the friction as well. And that was it. That we're about in time, and I don't know if you have any other question. We're open to do that, but hope everything went okay on your side. I think Justin had some little technical issues during the presentation. We'll be back tomorrow with some other topics. We'll be covering gas lift, plunger lift, gas wells. So we'll have a good number of examples tomorrow as well, and good information to cover. So thank you everyone for attending, and we'll hope to see you all tomorrow as well.